Okay, all the buttons have been pressed. We could start our meeting today. Good afternoon or good morning or good evening, everybody. I'm Ken Gracie with Parallax. Welcome to today's presentation, which I had a preview of yesterday, and it's really neat, so we want to get to it as quickly as we can. It's from Dr. Gavin Garner, entitled Teaching College-Level Engineering Mechatronic Courses with the Propeller 2. This is an open Zoom meeting, so anybody can unmute themselves, ask a question anytime. We might even defer you to the end. Before I let Dr. Garner loose, we're going to go back in time just for a minute. If you remember from last week's presentation from Johnny Mack, I threw out at the very end that if somebody brings us their SBUS applications or examples using his code today, that you could win a GPS module from Parallax, which is really good for an upcoming presentation from Johnny Mack in June. So do we have any contributions? Anybody? I have one here that I can share. James, do you want to go first, or shall we let
Sure.
Kevin? Okay.
I will do something. No, I will have to try to figure out how to share my screen.
Green button near the bottom, and then you'll have a lot of choices.
Yeah. This one. Okay.
Looks good.
So, can you see anything?
Beautiful.
All right. So this is actually P1 code. I'm in the process of firing up development again for P1 and then obviously P2 after that as well. And so you motivated me by developing some drivers and stuff. And this is how I develop for the P1. I do it in Visual Studio, and I have a emulation framework which I use, which allows me to debug and things like this. And I thought I would just use this opportunity to show you how that works. The advantage, of course, is you can run a whole simulated session, and it gives you a nice little tick box over here to say, yes, something happened. Okay, so let's drill in to have a little bit of a look what did happen. So if I debug this test, it's going to run this code, and I'll drill into that in a second. And I can get out what the result was and what the channels were decoded to, and compare them to what was sent. So this is just a standard unit test. Okay. So in this case, they were correct. We'll drill in again. So how this works is I have a framework, if you like, which in this case, the app is just the highest level thing. I'm not going to go into every detail. This will have to be another time. But I have essentially an API driver. If you come down to the bottom here, you'll see this is the code which I've ported across from Johnny Mack's code and converted that here. And the advantage, of course, is I can debug this if I like.
You want to rock on your toe.
Wow, okay.
So then I can debug and I can inspect the variable values and things like that inside of the framework. And when I'm ready to generate the code, I have an export feature, which I can then export this code. And then it ends up looking a bit like this. Which I'll have to just grab for you in a second. Where did it go anyway? Where did it go? Good question. It was open in that folder a second ago. Where did I even put that? Let me just grab that code. it is. So it exports it as spin code, which we can then compile and so on and use in our projects. So this ends up being the P1 version of Johnny Mac's code.
So Propeller 1, Johnny Mac's code ported to P1 in Spin and VSC with the debugging code that you've written.
Yeah, so I thought that might be just a nice little demo.
All right.
Quick question.
Yes.
This is, you have a, it looks like you have a C# interpreter for spin code that you're using to debug for P1 code?
Yeah, it's a framework which is built on top of C# and then it's got objects and things underneath. So this is obviously quite an extensive conversation if we're going to drill into actually how it works. But yes, it's a C# framework. So we have
we can talk offline about it, but I'd be very interested. Have you done a post about this framework at all?
No, I haven't. This is something I just use internally for development because it's a complicated beast, so to speak.
Sure it is. Sure it is. And it's a Windows only beast because of it, I think.
Right.
Unless you ported the C# to one of the frameworks for Linux or something.
Yes.
Well, that would all be possible, yeah. But it's just that it's so bespoke. Do you know what I mean? It's very hard. I haven't really considered about releasing it as a tool for others because it's just got so much embedded knowledge in how to use it. But
yeah,
it's something we could talk about. Yeah,
this is exciting. Congratulations.
Yeah, and thanks for thinking about the P1 along the way too.
Oh, you want to see something more then? I'll give you two more minutes.
Okay, we'll give you 2 more, and then I have something queued up.
Can you see? Are you watching this video right now?
Do share screen and then pick the video.
Okay, I have to do that then. Hang on a second. Let's see them there. Interestingly.
Should we come back to it, James, afterwards?
Sure, we'll come back to it afterwards.
Okay, good. So after we get through this part and then we hear from Dr. Garner, we can come back to anything like this too. So here's another submittal that came in. Actually, didn't really, I just harvested off of a message from Roy Eltham where he used an SBUS to PWM converter just to try out Johnny Mac's code. And well, the conclusion was that it works. Okay. So the next share up, I guess that would be Kevin. Kevin, you good to go?
So here's KevinBot 2. And I'm using the P2 so that the receiver will work on the Raspberry Pi because I don't think the Raspberry Pi can do inverted serial. So how it's sending the data on the different channels through this XB, and it gets received on the other XB that's connected to the robot through USB. No, the screen is hard to see. And
Pull back a little bit unless you're going to show the code first? Okay, good.
Oh, cool.
And this is the Python code. And yeah, I don't know. It's really hard to show, but it's just
Maybe show it.
unfortunately the serial library that works on a Raspberry Pi, if you read the whole line at once, it'll lag a lot. So I had to just read all the bytes and then put it into an array and then convert it to a string. And then after that, it'll get what's on the different channels, and then if it's the value at once, it'll do something on the robot.
And then tilt the screen back just a little bit so we could see the robot's head. Yeah, perfect. Okay.
You can use the throttle for the head. And you can use the switch right here for the gripper. I don't know, it's hard to see. Let's see if I can.
Yeah, it's
There.
super. We have a good view.
You can use these knobs for the arms. Yeah, I think you can see it. Even the half-finished arm, I need to get more servos to put it on there. And unfortunately, there's a problem with the power delivery in the robot where the light in the head will really lag behind. So you can use this switch here for the light. So now it's turning on to white. And it kind of lags when it blushes, but now it's set to pink, so it's blushing. It's hard. Let's move the computer so it can be seen.
Here. No.
Any questions for Kevin on this? This robot keeps growing by the week.
Yeah, I've actually tested the robot and made a video call and went a walk with the controller, and it'll actually work quite far away.
Super. And this robot is only awaiting a better motor drive system. And then it's going to be rolling.
I've also got a video on YouTube about it. I'll try to find the link and put it in the chat.
Okay, yeah, put that in chat. All right, so we've seen 3 examples of SBUS. And Johnny Mac, who wins this GPS module? Put you on the spot there.
Kevin, winner, chicken dinner. You got a robot. Robots rock.
Wow.
Robots need GPS. Put a GPS in the robot.
Thank you. Jump up and down whenever he's happy.
Well, great job. You earned it. And thanks, John.
That's my prediction true, too.
Thanks for sharing that.
Yeah, it's very inspiring. The only problem is,
Kevin.
Yep, we're out of stock of these, but we should have them within a week here. Good job.
Okay.
Okay, and coming up next on June 9th, we will probably have a meeting next week too. We just don't have a topic, but we'll schedule it anyway. Johnny Mac is going to unravel this sensor for us and show us an object. And I'll post in the chat right now links to all of that. So there's the Zoom link and then the link to the sensor if you want to pick one up. And then 2 weeks later, with a break in between where we'll have just an informal meeting, is the GPS module. So here's a link to the hardware if you want to pick it up, which is currently out of stock. Just put yourself on the wait list. And then a link to the Zoom meeting as well. And since we have educators here today, I've looked at the sign up. We have about 80 people who signed up, and a number of them teach different courses in high school and community college and university. So for those educators, we have a series of 4 workshops coming up spread across July, September, October, and November. And they are 3-hour-and-a-half sessions designed to move the student from the casual maker to one of having more engineering skill. And we are providing the hardware for these classes free of charge. Qualified teachers, up to 400 teachers will be accepted. And the applications are at this link. Most everybody who applies gets accepted. It's co-sponsored by cyber.org. So in this case, we're looking for teachers, middle school on up. And there's some, this will be run by Andy. And Andy has also produced a really neat tool called Cyberscope that runs in your browser. This is really fun. It's like a slow oscilloscope and voltmeter. So we are applying a lot of this engineering tool, and the microbit is much like the P2 is used, is the tool under use. So join us if you'd like. And for today, Dr. Garner, who we can call Gavin, he's been a Parallax customer for 20 years. And he was first using the BS2, the BacicStamp 2 in his program around 2002. And he's worked with several of our titles from Andy, What's a Microcontroller, Basic Analog and Digital, Process Control, among others. He has a bachelor's degree in physics from Colby College and a master's and PhD from University of Virginia in mechanical and aerospace engineering. So before he joined the university, he worked as a mechanical engineer for AMF Bowling. Can you imagine that? He'll tell us more about himself, but I'll just back up to December. In December, when the P2 hardware was getting finalized, he was the first to jump on it, and he bought 100 kits for use in his spring semester class. And he had not used it prior. He'd been following the FPGA images along for many years. And he put together these trainers and a curriculum. Now, can you imagine a professor doing that while the class is rolling? This is really quite a feat. So he asks a lot of his students, as I see from his presentation yesterday, and but he matches it with his own effort, which is tremendous. So what's interesting too is, like many people that show up on the P2 Live forum, we often don't hear from them. They read the forums, they watch certain videos, and they're using all of the great tools that our community's produced. The work from Chip, Jeff, Eric Smith, Johnny Mack, they seem to know all about it. And Gavin is one of those people. As he starts, he will mention that we're producing a kit together this summer. Thankfully, we've got him on sabbatical next semester. So we'll be turning his Mechatronics course into a kit, which we will produce in a box for release with 200 units by the fall. And the Parallax team will be working with him. So with much appreciation, pass this on to Dr. Garner. Are you with us?
Yes, thank you very much, Ken. Thanks for that introduction. So Ken had thought that you'd like to, maybe I'll fill in a couple gaps in my background that Ken might have missed just now, and then have kind of a virtual lab tour of some of the facilities that I use at the University of Virginia, and then go on to how I would work out these kits for a course I teach to all mechanical engineering students in their third year, undergraduate mechanical engineering majors, using the P2 and the P2 Edge, and how that was made, and how this might translate into building a kit through Parallax to base this book titled Exploring Mechatronics around, which, as Ken mentioned, we hope to get out by the fall. And then I'll go into some of the specifics of what I taught in this course this semester. So maybe 20 minutes for kind of a virtual lab tour and some great examples of Parallax products that we've used in various courses at UVA. And then maybe 40 minutes or so on kind of exactly what I taught in this mechatronics course to college level mechanical engineering majors. All right, and so I'll keep this fairly informal. So if you have any quick questions, please stop me. If there's some kind of a sensitive topic we might be discussing, like floating point, whether or not we need that on the P2, we'll talk about it for a second, but then we'll push it back to the end in the Q&A section, just so we don't get too sidetracked tangentially. So I will start with kind of a virtual tour of some of my labs. Actually, before I get into that, I'll fill in a couple more gaps. So Ken mentioned that I worked for AMF Bowling after graduating with a physics degree from Colby College. I was one course shy from finishing a music major as well. So I was a fairly well-rounded student at a liberal arts college. So I wasn't your typical engineer through undergraduate, at least. And then I landed this job at AMF Bowling in my hometown at their headquarters in Richmond, Virginia. And that really was fascinating for me. With physics, I had a good understanding of how things worked, and a basis in physics and kinematics. And the bowling pin spotter machines haven't really changed a whole lot since the 1930s. So they're beautiful examples of antique mechanisms in motion. In fact, I'm sure most of you have played the game bowling, all of the motions that it does, from figuring out from a pile of bowling pins and a bowling ball what the bowling ball is, sending the bowling ball back to the user, sorting the pins back into a triangle. On the AMF machines, all of that is just being run off of 3 induction motors running at constant RPMs. So it's just kind of mind-blowing, the linkages and the kinematics involved to make that happen. I quickly realized that that's probably not the way you want to design modern machines. And so that led me to go to graduate school at UVA to learn more about how to design machines in a modern context. And that led me to become an expert on mechatronics, which is what I'll be talking about, what I taught this spring. And so mechatronics is really an evolution of mechanism design away from really fancy shapes coming off of very simple motions like induction motors at constant RPMs and or water wheels or windmills if you go back even further, where you just take a simple motion and convert it into more complicated motions through shapes. Instead, now we just create the complicated motions using servos and steppers with microcontrollers like the P2 in the loop. So that's sort of the evolution of mechanism design within mechanical engineering. And as I'll discuss, I think the P2 right now is the best tool for incorporating into mechatronics prototypes and for teaching mechatronics. The parallel processing and the smart pins really just make it far and away unlike anything else that's out there in this price range. So, at UVA, I had an advisor who was very interested in mechatronics, and he kind of nurtured my exploring how to teach this. So I've been teaching ever since I started as a graduate student, as a teaching assistant, of course, at first, but then actually I was teaching courses single-handedly before I'd even graduated with the PhD at UVA. So once I graduated, they asked me to stick around and continue to do this. And I've had a lot of fun, learning how to become a better inventor by incorporating these mechatronics tools and ideology into kind of everything that I look at as a mechanical engineer. All right, so let's start with the kind of a video tour of some of these labs that I've created. Actually, I'm gonna share the sound just in case. All right, so this is the mechatronics lab, and I'll kind of give you an overview of what that looks like inside the building. If this is too choppy or I need to just do freeze frames instead, let me know. So this is kind of the hallway. This is a neat kinetic art clock that I built with the student group that I created called the Gizmologists, and they basically just make cool stuff for fun. So kinetic art stuff is a great example of what they do. So this shows the seconds with RGB LEDs, and then it's got these metal gears that are water jetted out of aluminum that show the time with LEDs behind them. So as it moves, based off of stepper motors and a propeller one chip, that's what it does. We've got a really neat jet engine that was donated by Rolls-Royce, a sponsor of our labs. This is our rapid prototyping lab where we've got some state-of-the-art 3D printers. I'll talk more about these later, but we've got Stratasys F170s, F370s, F380s, Fortis's, Objets. This is the mechatronics lab where I teach students typically about mechatronics. Because of the pandemic, I wasn't able to teach the students in this room this semester. It actually kind of became a mess because of the pandemic and random things I was trying to do to support the hospital last year. You can see electric guitars. That's sort of been a claim to fame using a ShopBot CNC. You'll see it's just a fun project I do in an advanced mechatronics course to get the students excited about G-code and also resonant frequencies and other, and from the electrical engineering side, analog effects pedal circuits. There's a little robot there. I'll talk more about that in a second. So a lot of people say engineers can't be very creative, but I think the electrical engineering, the electric guitar project really kind of flips that upside down, and the students get very excited about various shapes. But they also have to design the shapes to resonate properly using finite element analysis. This is the rapid prototyping lab. So again, these 3D printers are not your everyday kind of ones you'd find at home. These have a dissolvable support material, so they make any shape possible and kind of effortless. So a great example, this is one of the demos you can print with it. This is a Geneva drive that all comes out of the machine fully assembled because it has a dissolvable material that's in the air gaps. It just comes out of the printer with the cocoon of this white material. You dip it in a bath of sodium hydroxide for a couple minutes, and you take it out, and it's fully assembled and ready to go. So you'll see that I incorporated that into making these kits this semester as well, these fleets of 3D printers. I've got some of the older models downstairs. This is in the basement. This is called the MIL, the Mechatronics Innovation and Learning Lab. And we've also got the 3D Printing Club has a bunch of kind of entry-level 3D printers in here as well. They also help me keep these old Dimension U prints running. I'll talk more about this lab a little bit later. So this is where I teach a lot of the capstone design work, where if students can kind of learn how to use these tools and then get kind of let loose to come up with interesting design work. So I leveraged all this stuff as I was making these kits this spring. So having these advanced manufacturing capabilities help. So ShopBot 4-foot by 8-foot CNC router in the back, all these ABS plastic printers. These are some of the parts that I'd ordered for the kits. So I mentioned this kinetic art clock. This is the team that originally founded the Gizmologists. So they're making this. Again, it's all programmed off of Propeller 1 chip. And I like the clocks, and that's been a theme of what I've done with the capstones more often than not, because once you finish the course, once everything works, if it actually gets to that point, you actually have something to show for it that isn't just sort of a quick prototype they tear apart for parts the next year. This is another one we worked on this last fall, which was difficult under the pandemic conditions. You can see we had face shields and masks on while we were working side by side. This one shows the weather outside. So it's got this UVA rotunda theme. For those of you who don't know, the University of Virginia was founded by Thomas Jefferson, and he was an architect as well as a politician, and he came up with a lot of interesting things that our university is based off of. This shows the weather outside. It is using a Raspberry Pi to connect to the internet to grab metadata from weather.com, I believe. And then it has a Propeller 1 chip that is deciding how to move these motors. So we've got a DC motor with a quadrant encoder on the spur gear that is causing the rain to go away and the snow to be out. So basically it'll read whatever the weather is and then display what's happening on this clock along with the position of the sun or the moon with these LEDs. This basement lab doesn't have windows. This is actually kind of nice when you're working around the clock on some project, just kind of know what time of day it is, whether it's daytime or nighttime, and what the weather's like outside. So this is kind of cool. It didn't quite get finished before they graduated, and they're walking our lawn as part of the graduation ceremony this Friday. But I think they learned a lot in the process. This is a gumball machine we made a couple years ago that is basically kind of a game too, where you can use a little solenoid to hit the gumball up and try to get it into this little basket. Obviously, the University of Virginia is pretty proud of its basketball team, so that was a theme this year. So projects like this, of course, this is running. There are several Propeller 1 chips behind the scenes in this machine making it run. This is another example that used a Propeller 1 chip as part of a capstone design project. This is a tic-tac-toe bot that it's using Dynamixel servos, which I'm actually not a huge fan of after digging into this project. But they're basically servos where you can tune the PID controllers inside of them and run them through serial communication. So all this was programmed, even the AI that's the computer playing against you. They also incorporated some war games themes inside of it too. So it has a little voice that's talking from the talk object for P1 where it says, shall we play a game? And if you tie it, says interesting game. Yeah, you get the idea if you've seen that movie. This is a neat little robot with mechanism wheels. It's running off a P1. You can see very obviously in the center of it of the breadboard. It's being controlled via radio serial communication, RF, and that turned into this Rotundar robot. This is another senior project where we built water jets into a kayak. So we thought it'd be kind of cool to have a jet ski kayak essentially. And this was testing it. They worked out the computational fluid dynamics for this. So they actually optimized these 3D printed impellers inside of each of these engines. They're running off of big, I think 150 watt brushless motors that are meant for scooters. And again, all this is controlled off a Propeller 1 chip. And it also has these DC motors, quadrant encoders that are controlling the jets. So they can actually steer differentially by aiming these nozzles as it goes. So these are just some of the examples of projects I've done with the students based around the Propeller 1. So you can understand that I'm very excited to start incorporating the Propeller 2 into these projects. So this is just testing, kind of get an idea of how much thrust it can produce. This is actually testing it in real life. Unfortunately, they kind of misjudged how much weight their prototype is going to be. So the mass of this thing is so heavy that Newton's second law doesn't let them go very fast. But it's pretty cool they got this working. I loaned them my Eddy Line kayak, which is a pretty lightweight kayak, to mess around with this. So Kevin, check this out. This is a robot that our students built. It's all made out of metal. So we have a water jet machine that can slice through up to 6 inches of steel because it's got 60,000 PSI of pressure with abrasive garnet dust mixed in. So it's kind of like liquid sandpaper. So basically just pressure washes through, in this case, 1/4 inch aluminum to make all these parts. Another interesting thing about this robot is that we're deliberately using worm gears so that once it freezes in a position and you lose power, it actually can hold that position. So basically one-way transmissions throughout the robot. All this is being controlled off of Propeller 1 chip right now using the ClearPath motors by Technic. Those are kind of neat motors. They're DC brushless motors, but they can be controlled like stepper motors with a micro stepper driver. So you basically can just set a direction high or low and then just send them a pulse and they'll make a step, but they've got all the benefits and power to weight of a closed loop DC brushless motor system. So it's kind of neat. They're about $300 to start with for the NEMA 23 size. So a propeller one is controlling those. And then we've got another little, they put a head on it just to kind of make it look cute with this running off of RC servos. Of course, mechatronics involves a lot of mechanisms, and I'm fascinated by antique mechanisms. Again, a lot of this might have stemmed out of from my work at AMF Bowling, but I like kind of showing the old and the new, and how you can take something like a Geneva drive and replace it with a stepper motor, or in this case, a lot of these neat mechanisms like the Post-Lipkin. Sorry, I'm just going back to that. So this is making a straight line motion off a rotary motion. Again, in the old days, everything used to run off of simple rotary motions from water wheels, windmills, and that's really what a lot of mechanical engineering design was based off of. How do you create a simple motion and make it into something more useful, either intermittent motion or quick return motion, like up in the upper left, or back and forth motion. So I think all this stuff is fascinating. Unfortunately, mechatronics is making a lot of this obsolete, even though it's a lot more inexpensive and more reliable if you do something like this bottom right one, which is just using a DC motor and a quadrant encoder on a ball screw to mimic these motions. So this is actually meant to be a display for a science museum in Richmond, where it can, you basically just you choose which one of these three you want, and this system could make all three of these. So that's really the power of mechatronics, is once you've got a computer in the loop, you can just change things by changing software. And of course, that's how something like a 3D printer works. You basically have a universal mechanism that can move anywhere within a body, change how it moves every time. So one day it can print out a Geneva drive demo, the next day it can print out parts you need to be able to hold down breadboards on your experimenter boards. So that's really the beauty of 3D printers. Again, stop me if anybody has any questions. So again, this is running off of P1. You can see the code on the right in the background. So we've had a lot of success using the Propeller 1 chip in mechatronics over the last decade. We've also entered into college level contests. So this was a contest a couple years ago sponsored by the American Society of Mechanical Engineers, where we had to have a robot. This is remote controlled, but this is running off of a P1 chip. And this was meant to mimic the Fukushima meltdown, and having robots that could go in and do various things like push buttons. This was another older competition where we had to have various cars doing a relay, and a lot of these cars were powered off of Propeller 1 chips. This is a NASA-inspired, sorry, I got the music on a little bit, a NASA-inspired contest that they've done for several years now, and it's a robotic mining competition that they hold down at the Kennedy Center. And so we entered this for several years, and most of our entries are running off of a Propeller 1 chip. So this robot is basically trying to dig for ice crystals within the regolith on the moon or on Mars. The idea being it's in situ resource utilization, where you'd want to have rovers, autonomous rovers, get to Mars years in advance of humans getting there and spending their time digging up what little bits of water they can find in the ice crystals. And what's cool is that NASA's kind of crowdsourcing ideas. So they look to universities and college kids to kind of jump on board and come up with creative ideas. And the judges are actually the engineers sitting there taking notes on what cool ideas the students might have come up with, and kind of cherry picking those to put in the real rovers. And of course, the students love the idea that they might actually be helping to get humans onto Mars. Some other things, this is a Etch-a-Sketch that I used a stepper motor versus a servo motor, so DC motor with an encoder. And the students would write a G-code interpreter basically to be able to take, in this case, a DXF file, convert it to G-code, and then have their system draw something neat automatically on an Etch-a-Sketch. And then I've got some other ways that I've done these various teaching tools within my courses. So this was something I call the Mech mouse. My first iteration of this was actually way back, I think in 2005 with the BacicStamp 2 chip. So for about 7 or 8 years, we used the BacicStamp chips within our mechatronics curriculum. But then I switched over to the Propeller around 2008. So these little robots, the students are programming them to look for cheese, and the cheese happens to emit Aire radiation at 38 kilohertz that the detectors tend to like. And it can see the cheese through these obstacles, but the ping sensors, we have parallax ping sensors as the eyes, can sense where there's an obstacle and try to avoid it. So they try to work out code to get it to autonomously navigate the maze to the cheese. So again, all this is running off Propeller 1 stuff. So hopefully these videos are coming through okay on Zoom. I've got a lot of these on a YouTube channel. So if you want to do a search for Gavitronics on YouTube, you can find a lot of these.
Yeah, it's working well, Gavin. Yeah.
All right. All right, so some other ones. This is a, this was an autonomous missile defense where I had these little Nerf missile guns, the original USB-based office toys. And so these are connected to the Propeller 1 chip, and the students had to detect where these alien flying saucers were, and using this Aire distance sensor, and figure out how to aim and launch their missiles at. All right, and then this one is kind of cool. This is a 3D printed printer. So when I first got the fleet of Dimension U prints, I thought it'd be kind of cool to show the students how you could actually use 3D printers in your machine designs. And so I used them to create fully 3D printed printers. And these are 2D plotters all running off the Propeller 1 chip that the students had to program to use the ballpoint pen to basically interpret G-code to draw whatever they wanted. Another interesting thing about these trainers was that I was using different motors for each axis. So I had a stepper motor controlling the Y back and forth on this rack and pinion system. I had a DC brush motor with a quadrant encoder controlling the X motion on this lead screw. And then the Z motion, the pen up and down, was controlled by an RC servo motor. So you had the relative positioning of the stepper motor and the open loop of the stepper motor juxtaposed with the closed loop of the quadrant encoder system, but also relative positionings you had to home it versus the absolute positioning of the servo motor. So these kind of three staples of modern mechatronics that students really had to fully understand the pros and cons of all side by side to make their machine come to life. And another neat thing about having a 3D printed kind of platform for teaching, just for the teachers out there, is that if a part breaks and you've got lots of students sharing these, so I typically have about 100 students a semester sharing these at the end as a final project. A gear chips a tooth, I just hit print, and 10 minutes later I've got another replacement. So it's easy to keep these things going indefinitely, no matter how much the students sort of abuse them. Of course, that's also why 3D printers, took the forefront last April, at least in this country with the pandemic, just because all the supply chains were cut off. So the hospitals were saying, okay, can you 3D print masks? Can you 3D print ventilator splitters and stuff like that? So that's a Parallax logo that the students, they're so happy with the P1, they decided to draw that as their project. This reminds me that I'm excited to play around with Chip's debug screen for MIDI. As a former music major, that's something I'm interested in messing around with at that time. All right, so are there any questions so far about some of the ways that we've featured Parallax, particularly the Propeller 1, in our mechatronics and machine design curricula at the University of Virginia so far?
Just a quick comment. I'm really glad that all the folks at Parallax are getting to see the most awesome lab I've ever been to when you hosted a P1 educators course there. I got to see this in person, and it is really just as great as you see on the video, everyone.
Thanks, Andy. My Zoom is actually acting up. I might have to restart it. So if you lose me for a second, that's where I am. I tried to stop sharing and it's okay. I'm going to log out and log right back in. Oh no, it came back. Good. Okay. Thank you, Andy. It was really nice having you visit a couple years ago and to be able to show this stuff off. it's again, Parallax has really done a lot for education within mechanical engineering at UVA for sure, but I'm sure at lots of other places. All right, so I was very excited for the P2 to come out, and I have been following its development for many years, and with the FPGAs and with some of the earlier iterations. And at this point, once we finally had the P2 Edge available and it looked like we're officially releasing everything at the very end of last fall, I said, okay, this is the time to do the plunge. And that coupled with the pandemic sort of created this perfect opportunity to justify going all in and trying to make 100 of these kits to ship out to each of my students to be able to use. They could safely work at their own homes. But I've always thought for many years that it would be really nice if I didn't have to have the students just kind of in an assembly line coming through the labs each week and doing a 2-hour cookie cutter lab to just get out and then have the next group come in. So they only had about 2 hours of kind of one-on-one time with the equipment. So instead, get the equipment in the lab out into each of their dorm rooms and apartments and really give them the time to dig in and absorb the material we were covering. So that's worked beautifully. And it was a major undertaking, as you'll see in this next kind of video montage, but it was worth it because I think this was the way to teach this stuff. And from here on out, even hopefully the pandemic's not an issue next spring and we're just teaching everything in person, but I'm still gonna be sending these kits home to students. Another funny thing is that, particularly on beautiful spring days, the students are always like, well, can we have lab outside? And they're normally joking, but now that we've got these things, you can hook a little lithium battery up to them. We actually could just take the labs outside. So that's another bonus perk. All right, so I frantically, in January, decided we're gonna make these things, 100 of them. I leveraged the laser cutters to print out the bottom plywood boards. And as you just saw, I designed all this in SolidWorks first to make sure everything was gonna fit. I laser cut the top boards. I could etch in logos and numbering on stuff on them and explaining what the various input jacks are and various features. So that was nice. We decided to use wood just because we could get that rather easily. These are probably way more expensive than we'd like to make for the Parallax kit, just because I don't think people want to spend however much with labor this would cost, probably $1,000. But so I'm thinking we might make an injection molded type part, something a lot lighter weight, but also robust. So that's something that Ken and I are going to work on this summer, trying to nail down exactly how we can distribute this easily. For the 3D printed parts, we leverage the rapid prototyping lab, again, using the fused deposition modeling machines with the dissolvable material, which you can see in white here. So right now it's printing out these little breadboard hold downs. And just being able to print these things and get 100 of them within a matter of a day or two is really nice. I also have an amp meter that I used 3D printed mounts to be able to do, and that let me add nice features like having a little screwdriver holder built into the amp meter, just as an added. I mean, if you're going to 3D print something, you might as well make it fancy because the machines can print anything you want. I tried to make these look kind of retro and steampunk, retro futuristic with the old school kind of wood antique quality with also the bleeding edge state of the art, Propeller 2 chip. So it's kind of fun to see that all come together. And I think the students really appreciated the kind of art aspect of these, and they really, I think, treated them with a bit more respect because of that. But I spent a lot of time in January and February making these things pretty much single-handedly. I did have a little bit of help from a machinist during working hours, but a lot of late nights, soldering, in this case using dipping parts into tin the solder, the stranded solder, to tin the stranded wires, making various parts. So this was a huge undertaking, hundreds of hours. But again, now that I've done it, I think I'm going to be using these from here on out because it's pretty modular. It's easy to replace things like breadboards if they go bad, get wires stuck in them or have an IC melt into them. They can all come apart. And I'll talk about some of the features on this that I'm proud of in a minute. So assembling all these things, I was able to come up with an auto tapper that we could hook into a mill to be able to tap the acrylic. So everything just kind of bolts in really nicely. Kind of see the 3D printed parts. And
just doing a quick check to see that everybody is seeing Gavin's video in large format. Is that the case?
Yep, I can see it.
Yes.
Looking great.
Great.
Thank you.
So a lot of soldering. This is actually something I'm kind of proud of that I'd like to incorporate into the kits. And Ken and I were discussing how we might be able to do this, but they've got these really nice relay breakouts, just single hole, double throw relays with a little transistor to give them a boost from the 3.3. And what we do is we cut these off. So we might figure out a way to automate these on some of the CNC machines that Parallax has or that I have. And being able to actually see the mechanism inside of these, I think really helps students to visualize what's happening inside of mechanical relays. So even the mechanical engineers I've found have a lot of trouble visualizing this, but actually breaking it open, showing them what's inside of the little blue box really helps them to grasp that concept, which I think is pretty fundamental. So things like this are the extra step that we're going to try to add to our kits to really make it something special and unique. Of course, I had to assemble a lot of parts for this. I'll talk about some of the components we use in the bill of material as well. But at the end, we had 100 of these things, and every student had one of them. Some of the students were taking this course from all over the country. I had one student that was in Serbia for the first couple of weeks, but I was able to wait until she got back stateside before I gave her one of these. But it's just really shipping these things out all over the place. And but then a lot of the students were on grounds at our university, which was nice because then if there was a part that was missing or broken, they could just come by a central location and pick it up on their own. So the logistics of that are going to be interesting as we create these kits, but that's one of the reasons why Parallax can help, because they can just be the go-to shop for getting replacements as students need them. All right, so that's the Mechatronics experimenter board version 1.0 that I used to teach my survey mechatronics course to 87 mechanical engineering majors at the University of Virginia. So I'll go into the exactly what the curriculum looked like in a minute, but any questions about kind of that process of making these or where we're going with this? All right, I'm going to try to stop sharing again. Great. Okay, so I can walk you kind of through some of the features of this board if you'd like. Okay.
Yep.
So obviously front and center, we've got the P2 edge. This is really remarkable. And it really, I could tell when I was looking at this back in early January that this was the one I've been waiting for. And it is, it's been incredibly robust throughout the semester. I was incredibly worried about students burning up pins, partly because I've got an entire Ziploc bag full of burned out or wounded soldier P1 chips because the students just aren't careful about, these are mechanical engineering students. They don't fully understand electrical engineering. And they tend to be kind of like a bull in a china shop when it comes to, conceptually realizing you can't just short things out and be careless in electrical engineering.
Are you showing an image right now?
Just on my video feed.
Okay. I have you spotted, but I don't actually see that image. Maybe the others do.
When that's in the video feed.
Okay, I'm sorry. I'm gonna
just gray.
We don't want to miss a thing here.
Got it. Yeah, I'm gonna try to. I might have to restart Zoom.
No worries. I think Zoom may even be misbehaving because it's showing Greg's avatar, but he didn't actually say anything and he's been muted. So we'll see if it sorts itself out.
All right, sorry about that. Hopefully I'm back.
This is good, yeah.
All right, so this is what I was trying to show off. So this is the kit, the P2, again, the main star of the show, and the P2 Edge module, if Michael's on. This is really beautifully designed. So Michael and Chip, congratulations on this. And I understand you're making an even better version with extra RAM and some improved power supply. We were just running everything off of the 5-volt USB, didn't have any problems with that. I like that because it lets us use these off-the-shelf lithium-ion battery packs that are really nice. So that lets it switch into robot mode. One of the tricks with that though is I wanted to be able to have a variable power supply. So in my lab that I've been teaching the students for years with, I've got beautiful top-word power supplies that are $500 a pop, and Tektronix oscilloscopes that are $1,500 a pop, and function generators and all that stuff. So one of the other things that's making this possible is the fact that the P2 has these smart pins that can let us do stuff like that. So it might be interesting to try to see if we can have some kind of a switching power supply based off one of the smart pin modes that runs off the P2 chip. I got these, this is a little boost converter you can get off of Amazon. It's nice because it has the display as you adjust it. Actually, I took off the trim pot, desoldered that, and hooked it into this larger pot so that students could use this to adjust their variable power supply. Really good in theory. In practice, I ran into some problems. For one thing, I wanted to go all the way down to much lower than 5 volts. So I actually put a boost on the back to ramp it up to about 13 volts, which in theory could go up to 24 volts, and then bucked it down off of this potentiometer. I haven't had time to fully debug what was wrong with this, but I think one of the problems I had, because I really tested the heck out of my prototype, but then for the mass production, I got cute and decided I was going to hot glue the wires down to keep them from breaking off. But I think that extra heat messed up the switching mode chip, and and these actually can't start up under any kind of a load or causes a problem. So I'll work out those bugs for the final iteration that we create, but it's just kind of nice to be able to have instant variable power supply for super cheap. Also, everything runs through this illuminated power switch, which is nice. So if things start shorting out very quickly, this dims, that's a sign to the students that something's bad. Usually the power will dip on the display here. And then we also have this nice analog amp meter. So this is also really useful, particularly for teaching the mechanical engineering students, because they don't really conceptually understand current flow. When they see this thing spike, they can say, oh, I'm doing something horribly wrong. So just having that visualization, I think, is a huge safety device. Other safety devices, I incorporated fuses on the back for the various branches of the power supply. So there's one for the P2 edge module. There's one for the 5 volts on the board, which also splits off to 3.3 volts, which I had a separate regulator for, because again, I was terrified of them burning up these $50 P2 edge chips. I'd much rather have them burn up a $3 linear breakout board for 3.3 volts. And there is also a fuse for the variable power supply. So we did blow up a couple of fuses here and there. This was kind of done at the last second just because I found I can get these on DigiKey, but these are actually inline little fuses, disposable, they're painted green, so you can't really tell visually when they blow. But I put these in line with the pins we use most often, pin 0 through 3. I wound up using 500 milliamp fuses because as you get down to these lower value fuses, the resistance really starts to spike up. So if I went with like a 100 milliamp fuse, it would have been like 10 ohms, and that might have messed up some of the signals coming out of these pins. But that's one thing I was really trying to protect. And as far as I know, I don't think anybody blew up the pins. I did blow up one in just trying to see how horrible I could be to these when I was testing things out in January. But so far so good. This is a very robust system. So congratulations, Chip, and for doing your due diligence and testing this thing out. I wouldn't expect anything less from Parallax, but these things have really been, they've gone through the ringer and come out on the other side.
That's due to Michael. I'm kind of reckless. But
I mean, the layout of the smart pin pads and stuff is really clever engineering. But another brilliant thing that Michael did that kind of immediately sold me on these things was putting the through holes on the backs of these LEDs for pins 56 and 57, so you can see them from both sides. That's just kind of an extra really brilliant touch that I liked. So well done on this. You notice I put a little heat sink on here. This isn't really because we need a heat sink. It's just because I thought the Ferrari red anodized aluminum just made this thing look like the Ferrari that it is, and the students kind of picked up on that. So you can tell them, using an Arduino Uno is kind of like driving a Honda Civic around. Using the P2 is a Ferrari. It's really probably more powerful than you need, but it's pretty awesome to be behind the wheel of this thing. A very large breakout board, no offense to the Johnny Mac board, but I think having a large breakout board really helps with the circuits we're doing, particularly trying to get the students to be neat and organize things and spread things out. And these are not electrical engineers for the most part. So another just neat little tidbit of information is I found these right at the last minute on Amazon in January, but they're LEDs that have a current limiting resistor built in. So you basically just have the LED, you don't even need the current limiter. Of course, you can't adjust the current limiter, but that's just kind of a nice FYI, they've got those now. All right, any other questions about how this is laid out? You notice I pulled the sticker off of the Parallax P2 bags and stuck them on the back, because I think we should be proud that this stuff's made in the US, for those of you who are American. Any questions?
I kind of have a question. Have you thought about, programming with like a console PC? It's always, it means more stuff, but I've always kind of tried to think, but I don't know how to think about it, but being able to take what you have in your hand and programming it somehow just as it is with we need some kind of extra interface. And, text on a screen allows you to see what you're doing. So that's hard to replace, but it would be really cool. Cause I used to think a long time ago of just making like a little 6502 single board computer and being able to like ride my bike all over the country and then stop and program it, but I wouldn't have had a monitor or anything. But we need some kind of system that can incrementally bring people up like a video game does. When you start playing it, it shows you how the controls work, what the moves are, and then you get pretty adept at it and you add to your skills. If we had some way to program micros like that, that'd be awesome.
Absolutely. And one of the problems I had in trying to distribute this across 87 students, even though as engineering students, they're kind of warned as when they're coming into the university that they should get Windows PCs. A lot of them have Macs, probably 20% or so. A lot of those were able to dual boot and run the Propeller tool no problem. But for the other, I think there were 4 or 5 in the class where I had to loan them a Windows PC. But on that front, they make single board Windows PCs now for around $100. So the Latte Panda is one you can get, the older versions of that. With a Windows license. So for around $100 to $150, you can get a decent Windows PC that can easily run the Propeller tool. So that's one possibility, but most students have some kind of an HDMI TV. So having an HDMI output to that interface would be beautiful if that were possible.
Yeah, I don't know if you've hung around the discussions much, but we've talked a lot about making like a self-hosting system, you know, to completely circumvent the issue. But then I kind of think the drawback is that people already have their monitors on their desks, and they'd have to be, you know, dedicating new equipment that they already have, like keyboards and mice and monitors to this. And it'd be nice because if you could work on the chip, everything would be super snappy and responsive. You know, there'd never be these weird delays that we have on the PC. And that's what's missing in the whole new way of doing everything is you don't have the old feel where you have immediate feedback like it used to be on old computers.
Yeah, I agree. That would be a home run. I imagine that would be a bit of work, but that would really be cool. And with the HDMI screens, like the ones that Parallax was distributing a couple months ago, you know, coming down the little ones, that might be possible just to have, you know, this kind of become a little laptop where you've got the little, you know, 7-inch screen that pops up that lets you program right on board. But I think, you know, the Propeller tool and the debugging options we have now are really neat. And so I think that brings a lot to the table with the Propeller tool. I'll talk about some of the things I use that for. I think you'll get a kick out of the video games the students made on this, so stay tuned. Any other questions about this board and kind of where we're going with this idea? Another aspect of it is to be able to convert it into a robot. So unfortunately, I bought a whole lot of equipment back in January, kind of trying to anticipate where I might be able to go to give me some flexibility. I bought these cheap, I mean, ultra cheap, like $2 a piece, plastic gearhead motors that run off of DC brush motor, and they come with the wheels too, which is nice. So I thought I'd be able to turn these into mobile robots, but because of all the extra weight of the wood and these really cool steampunk casters I got for making it into a kind of a Bobot type machine, it just didn't have enough power, and I also was running out of time. But the idea was to try to turn these into mobile robots for this semester, but that's something I'm gonna have to wait until next spring, or this kit we're building over the summer for. That would be the idea. It's modular, so you'll be able to plug things in. On this, I just had little thumb screws that they can use to take these things on and off. We also could add things for convenience, like potentiometers to the front of this, for example. So if you're doing an experiment with a potentiometer, you just kind of use the thumb screws to put this on for a single turn or a multi-turn pot. So just, it makes this kind of a transformer that turns into whatever you need it to. I was thinking about putting, you know, a ping sensor for the eyes and on a servo, this thing turned into a mobile robot. I'll talk, one of the things I wasn't able to get to, there were a lot of things I'd really like to have done if I'd had more time and money, but to put the wheels in the center and turn it into an inverted pendulum kind of hoverboard style robot and try to incorporate some PID into the curriculum, which I used to have based off of these really fancy industrial servo motors with analog tachometers. So that's one thing I still have left to do for this book, is come up with a good PID system. And that gets into the floating point can of worms. If Eric Smith is on the line, I did actually dig into some of the floating point objects you've posted on the forum, and I was able to get those to work, and those are nice with the binary IEEE 754 standard. So I'm a proponent of sticking with that. Whether or not we can actually incorporate that into the Spin2 syntax with having casting and stuff, that's less important, but having some kind of very reliable floating point would be useful for things like PID. Is just a great example, whereas in engineering we use that all the time, and just having floating points makes your life so much nicer.
Hey Gavin,
yeah.
How much resolution's needed? Do you think 32-bit is sufficient, or should we do like a 64-bit with a much bigger mantissa?
It depends on how long it's going to take. So if it's just interpreted spin, then even on the P2, that it might be 64 is going to take longer, depending on how many 32-bit instructions it has to do along the way. So in most control loops, I'd say we want to have about 1,000 iterations to the loop per second. So it has to be able to do a couple floating point calculations within a millisecond, which shouldn't be a problem. whether or not it has to have a dedicated cog and stuff, I'm not sure. But I'm happy to work with you this summer, try to nail some of this down.
Yes. Have you looked into that posit? I think they're called maybe posits. It's an alternative to traditional floating point. Are you familiar with this at all? I am. The base 10 base stuff. Is that? Oh yeah, we could do the base 10 thing. That's yeah, Eric's got that working. Yeah, I heard, I did catch some of that recorded YouTube video. Again, I haven't had time to just sit through all of these live, but I've been trying to catch up on trying to watch some of these recordings. So thank you, Ken, for putting these up. That's very useful, as he mentioned in the beginning. I really think that IEEE 754 has to come first and be obvious, and with parallax supported libraries for that. But I think if you after that works, if you want to try other things, I don't think you should make the base 10 one native to P2 and spin 2 is my gut reaction. I would, if anything, I would make IEEE 754 single precision native. Yeah, that's what we had working on the P1. But it still is through method calls, which when you get into, you know, a PID algorithm, for example, things get obfuscated when you start having a whole lot of FAD, FRound stuff. Oh yeah, no, that was poor, but yeah. The advantage, I don't know if you heard this, but of the base 10 thing is, you know, when people are using floating point, they tend to get really strange rounding effects and things that they just kind of makes them scratch their head. If we stick with like a normalized, or what would it be, 10 million, right? Then the kinds of mathematical errors you get tend to be in least significant digits, as opposed to, you know, just making a crazy looking error. The crazy looking errors typically happen when people forget, because there's no casting, and they try to multiply an integer by a floating point number and get a billion or negative billion number, and they're scratching their head as like, what does this mean? Because they're trying to look at an IEEE 754 format as an integer. And that's where all the mistakes come from in my experience with the students. So that's where, you know, something like C or Arduino C just instantly, you know, casts it into a floating point if you try to multiply an integer by a floating point. But I understand that having variable types is really going to mess with, you know, making spin 2 very complicated. Well, yeah, we need to really look into it. Maybe there's kind of a hygienic way to achieve it.
Okay.
Yeah, I bet yep.
We'll let Gavin go on. We can come back to this.
Okay. Yeah, I think this is a great topic, and it's something that's very important.
Let's not get stuck on floating point.
I foresaw this as one of the sticking points, but this is fun. All right, so that's basically the kit. Any other questions about kind of the hardware that I threw together? Again, I tried to make these kind of look kind of classy and worthy, so the students wouldn't just totally destroy these. And so far, so good. I got most of these back so far. A couple of them are still being shipped to me. I got a FedEx just a couple minutes before this meeting, with another one coming from all the way across the country. All right, so next up, I'll talk about the actual curriculum that I established for this third-year mechanical engineering course in mechatronics. So particularly for any of you that are teaching college-level engineering, this might be interesting. But for those of you teaching, you know, high school robotics and or community college level engineering courses, this is probably interesting. So I had to stall a little bit. This is the schedule because it took me a while to make all these, like literally 400 or 500 hours. But so at the beginning, I kind of had warm-up stuff. And actually, there's some of this that I like doing. So I think some of you might be interested in this, particularly using TinkerCAD. And especially for teaching the mechanical engineers the basics of electronics, this was actually very useful because it doesn't cost a thing when they blow something up in the virtual TinkerCAD environment. So TinkerCAD, for those of you who don't know, is owned by Autodesk at this point. You know, one of the juggernauts of software when it comes to engineering. So they run Inventor and Fusion 360, and they own Eagle now, for those of you who've designed PCBs with Eagle. And one of the beautiful things they do for the education market is for all students and all professors and faculty and teachers, they let them use their software for free. So you can just download Eagle for free. You can download Autodesk Inventor, which is typically like a $5,000 program, for free while you're a student. But then they also they're very active about policing people that then continue to use it in the professional environment after they're students. So be careful of that. So for TinkerCAD, for those of you who haven't seen it, you can basically simulate circuits, and they even have Arduinos and Arduino C built in. So as much as I hated to bring Arduinos into this curriculum, I did just because I could let them use this in virtual prototyping while I was trying to get the P2 stuff in hardware out to them in person. So what I had them do was design as a project a Mechatronics system. So for those of you who aren't familiar with Mechatronics, again, it's sort of an evolution of mechanism design away from shapes into microcontrollers and smart motors. So in this case, for a Mechatronics system, by definition, you need to have a sensor and a controller, or microcontroller, and an actuator, some kind of a motor system, something moving. So in this case, I wanted them to design something I thought would be useful for the pandemic, where they have a timer that they can hook up to a sink. So when somebody walks up to a sink, it times them washing their hands for 20 seconds, just like Dr. Fauci has told us to. So the idea is they'd step on a pressure sensor, and then they would have a ping sensor detecting the hand underneath the soap dispenser, which would then move this motor, which they would imagine was connected to a pump, and then have these 7-segment LEDs count down from 20 seconds. I had them running this on the Arduino, but I basically had them using essentially Blockly, so the blocks code. So they weren't even digging into C, but it does show the C equivalent as they went through this. So this again was just kind of a warm up. But this does work pretty well. It's kind of cool. They have the parallax. You can see the parallax logo on here for the ping sensor. And it works pretty well where you step on the sensor, it detects you're on the sensor, and then it detects your hand underneath the ping sensor. It starts moving the motor. And with luck, it should start counting down. Anyway, usually the LEDs will start counting. So it'd be really awesome if someday we can get Propeller 2 incorporated into something like this, but I think that's a ways away. All right, so that's just an example of what you could do with TinkerCAD. We'll get to that in a second. So then I got into the actual, the lab. So I'll kind of walk you through some of these lab experiments. And some of these are kind of let's start with this. This is excuse me. This is a list of the various things I cover in this course. So you can see there's a bit of electronics because this is the first time the students have actually seen most electronic concepts. So things like Ohm's law, they might have seen in a physics course, or the power law, but really digging into the applications of this stuff: analog to digital conversion, digital to analog conversion, pulse width modulation, H bridges, relays, resistors, capacitors. And then the mechanical engineering side, how do we get these things moving with the actuators like servo systems and servo motors and steppers, solenoids, things like gear transmissions, various types of lead screws and ball screws. And then it's a little bit of computer science. At this point, most of the students have taken an introductory course in Python in their first year. There has been some interest within the engineering students to take a MATLAB-based programming course instead. I take the stance on programming where it's kind of like riding a bicycle, and it's something that the students just kind of need to get a knack of how to think of it. And it's not so much important what type of bike they're learning how to ride on. So it doesn't matter if it's a 10-speed or a mountain bike or a flat tire bike or something. It's just getting the balance and understanding what's going on, understanding how if statements and for loops work and how to structure things and how to start thinking like a programmer, I think is the most important thing. I actually got started in programming back in high school when in the 90s when we had these TI calculators, which some of you might know. But these were great because I could sit in class and be working my calculator, and the teacher thinks I'm working. But really, what I was doing is programming games in BASIC on these, and even dabbling in assembly on some of the other models of these back in high school. So I kind of taught myself how to program in BASIC on these calculators just because I could program games like Tetris and Snood and stuff on these during math classes, which then hurt me in college and graduate school, and I actually had to know what those math classes were about, but it was fun at the time. You'll see that I use video game programming as a kind of a lure to get the students more involved, in this case in Spin 2. But I think unless the students are gonna become computer scientists or software engineers as a career, at this level, it doesn't really matter what language they're using. And computer programming languages, you know, the big ones like Python and Java and C, they're all hardware agnostic on purpose. And in mechatronics, everything has to be involved the hardware because that's the whole point. So it's kind of like two different ends of the spectrum in terms of what computer science is for. So you want to be able to tell computers to do stuff, but in computer science courses, it has nothing to do with the capabilities of the computer. Whereas in mechatronics, everything is about the capabilities and what you can squeeze out of a microcontroller chip. So I think that that's one of the reasons why Spin 2 really works well, I think, for microcontroller programming for mechatronics, because it really takes the hardware into consideration and it works perfectly for that. And it also kind of cherry picks a lot of really nice things from various languages like indentation and status scope brackets and And the new inline assembly is something that's really cool. That's something I'm starting to dabble with, but that's exciting. All right, so any questions about kind of the overview of what this course is supposed to cover? It's meant to make mechanical engineers dangerous in terms of making modern things move in the context of learning a bit about electrical circuits and computer science to be able to make mechatronic systems come to life. All right, so as I mentioned, I started with the TinkerCAD, so I was able to just go through some basic electronic stuff, even starting with stuff as cute as just trying to make little batteries out of lemons, which some of them probably did back in lower school. I don't know, is Kevin still here? Kevin, have you ever made lemon batteries? Anyways, I'm sure some people have.
Yeah, no.
All right, something to try. It's really not expensive. It just costs a penny and then a lemon and a zinc wire, a zinc nail. So that kind of walks them through. You actually, Kevin, seriously might want to play around with TinkerCAD. It's free just to sign up for, and you can it's a great way to kind of dabble with electronics. So I walk the students through the basics of how potentiometers work. Again, this is really nice because if anything blows up, it doesn't cost me anything. It's just, it shows a little spark in their simulation. But again, I did this as sort of a punting exercise. I also got into logic gates as the basics of how you construct logic gates with transistors and integrated circuit chips. So the 7400 chips to be able to make, I think we did a binary adder. So that really helps them to conceptualize what assembly program is doing too. So building up on this stuff really from the ground up helps them to kind of see how it all fits together. So they built a little binary 4-bit adder system. And then, as I mentioned, they did this hand wash timer project in TinkerCAD. But then we dug into the Propeller 2 stuff. So let me get on to that. All right, so this is kind of a preview of stuff that will probably be turned into this textbook that Ken was talking about. So introduction to the basics, how the circuits work. We start with the traditional stoplight, kind of a tip of the hat to Andy and what is a microcontroller. So they built a little stoplight. To me, that's the hello world of microcontroller programming. So it's just kind of, everybody has to blink an LED. This is the first thing they do on a microcontroller chip. And I deliberately try to start with something very simple. So I actually really like Chip, the pin high commands, rather than having to go right into direction registers and output registers in the very beginning. So this is nice. The Arduino C has had something like this. So this is a great way to start. And I love the way too, you can do lots of different things. You can do the shortcut pin H instead of pin high. And I like that it sets the direction and the outputs in one swoop, because that's nice. That said, I do actually go into telling the students how the registers work, because I think that's fundamental to pretty much all microcontroller programming. So we do get into that lower level detail as well. Same thing with the clock. It's nice to have the wait milliseconds, but it's also nice to be able to jump in and get the count when you need to, as well as getting the seconds. That's nice too. So basics, understanding voltage dividers, experimenting with that. I did have a multimeter in the kit. I did a lot of experimentation. I like this little $15 auto ranging multimeter. But another thing I'd really like to try to do with Chip's help is, and this kind of ties into what Andy was showing with the cyberscope, and I think there's a multimeter inside of that MicroPython environment too, is having some kind of a P2 based multimeter and oscilloscope and logic analyzer built into the system we're selling, because that saves a ton of money. But that might incorporate other fuses or buffers or other things we may have to do in terms of hardware.
And we could even make it programmable. It could be the P2 as well.
Yeah, that's the idea. It'd be coming out of the P2 and the debug screens. So that's something I'm excited for. That the lower we can get the cost, the more this will be accessible. So I mentioned that the cutaway of the relays is kind of nice to visualize that. By the end, as a grand finale in this first lab, they built a complete mechatronic system. So as I mentioned, you have to have a sensor, a controller, and an actuator. So I really want to bring that home at the beginning. So I used these little cheap DC brush gearhead motors, and I 3D printed, or sorry, laser cut these acrylic mirrored pieces as a crude encoder disk. And I use these little Aire distance sensors. These are kind of nice. You can get them for super cheap off of Amazon. They have a little comparator on board and a little potentiometer you can use to set the reference voltage. It's a 5-volt system and has the Aire LED and the photodiode. And so you basically just set the threshold and it will output a digital 5-volt or 0-volt, depending on whether or not you're above or below that threshold. So super cheap, super nice. So I use those first, just a single one to make an incremental encoder. Encoders are obviously a major part of mechatronics. And in this case, they detect when the system moves past one of the fins of the disk, goes across and breaks the beam or reflects the beam off the mirror. and then it decides to move the relay on, so it turns on the motor. So basically it creates a Geneva drive in a mechatronic system rather than a mechanical system. So it does an intermittent start stop, and that kind of shows everybody what mechatronics is all about. All right, then in the next lab, I got into, each of these labs took a week. So the students were able to work on these. I did a Zoom live session with small groups of about 20 students at a time during the week. But then if they didn't finish anything during that time, they could work on their own because everybody had a kit at their house, which was nice. We get into the Propeller 2 architecture, this neat P2 Edge module board, and a little bit more in-depth details, digging into what direction registers are and output registers and input registers. Dig into a little bit more of the timing. This is one of these little things, I think I mentioned this to you, Ken, a couple of weeks ago, but something as simple as just being able to disable the F11 key would make a huge difference. And again, part of that Ziploc bag I have of dead P1 chips just came off of the fact that the F11 key was right next to the F10 key. And so what I do as a safety feature on these boards is I have the students program into the flash on the P2 a simple program that only blinks, in this case, pins 56 and 57. So it makes it very obvious when the chips reset. Because a lot of times in mechatronics, we're driving inductive loads like solenoids or motors and off a battery, and we'll have a dip in the voltage that causes the chip reset. But when you're trying to debug new code and you don't understand why the code is doing something you weren't expecting, and not being able to know it was just a simple reset is a big problem. But furthermore, as the students are going through these labs and every day doing something different, if as soon as they turn on their chip, it starts running some other program like the stoplight I just showed, that's turning on pins to output and trying to send voltage and current out from them. And if it's going to something else, some other type of circuit, for example, if you have a button hooked up that's just going straight to 3.3 volts and you have it starting out as an output and going low, that's going to send a lot of current through the pins and burn them up. So what I'd like to do is have something in the Propeller tool that just lets you disable the F11 key, so that once you've set something to the flash, it's going to stay there and you won't carelessly overwrite it by mistake. So what I did as a mechanical engineer as a solution in my labs was I just pried off the button on top of the F11 key and stuck a little 3D or laser cut piece of acrylic underneath it so you physically couldn't push it down. But when everybody had their own laptops, this semester was something that was more difficult. Anyway, so these are little tricks from within the trenches that I might be able to throw out that might be able to help other people in similar situations. All right, so we got into some more of the details of how the P2 works and how you can, for example, use the get count rather than the pauses, because that happens a lot in mechatronics. We want to have more control over what's happening. So I like kind of being able to go back to the P1 approach for timing when you need to. Plus, I just think the more the students can conceptually understand what the microcontroller is doing, the less they kind of look at it as some kind of a deity they have to appease, even though they don't understand it. It's just, I like them to have the agency to understand what's going on. And that gets us into the assembly too. So obviously parallel processing sets the Propeller 1 and Propeller 2 apart and is really convenient for mechatronics where you can just kind of dedicate different cogs for different tasks. And that coupled with the smart pins now really makes things, lets you juggle a lot of things at once. So you've got 8 parallel, very powerful CISC-based 32-bit processors. On top of that, you've got 64 smart pins, which are actually little baby processors that can do things like generate PWM signals or analog inputs all on their own. So it's kind of mind-blowing how much stuff this can do at once. Get them into understanding how methods work. All right, so, and this is kind of cool. I worked out, this is a PDF, so I can't show the GIF, but this is actually a GIF that shows you kind of a visualization of assembly. So I dig into assembly. This is a program I worked out for a stoplight. So basically just turn on pins 0, 1, 2, and 3 for a certain amount of time, but actually walk through thinking of the processor like an elevator where it goes down and grabs the whatever bits they're using for a certain pin state and then deposits it into the direction register and the output register. So it's kind of cool to kind of visualize that. And then what else I did was I juxtaposed 3 different levels of assembly essentially. So we've got the PASM2 to run this. And then I also did it with the address, the COGRAM addresses. So they can kind of understand it's going to basically copy whatever's in address 12 and stick that over into address 506. And then of course I've got the opcode, the binary that work. And another cool thing is I was actually able to run this. So Chip, I don't know if you ever tried this, but you can actually run this code by itself and it just, everything compiles and runs just fine. So.
Yeah, that would work. It just runs over them and executes them.
Yep. So this works. It's kind of cool. All right. So then we got into, so Johnny Mack. So John, thank you for working out all of these wonderful starter codes. We used the easy analog a lot this semester. So in this case, we're just reading a potentiometer value and converting from 0 to 3,300 for a 0 to 3.3 volt signal. So we get the nice voltage units coming out of this. So thank you for the help with this. This really saved us a ton of time. So for those of you who don't know, John has worked out a lot of starter objects for people to just be able to tap into. And this is just a huge service, so thanks. All right, so then at the end of this lab, they had to make a video game. So this gets kind of fun. So I had them using the debug commands. We hooked up a button, and I gave them some starting code that basically made like a Space Invaders type game using the debug window. And I gave them some tricks and traps. And I've actually got a whole lot of these that I'll work with you, Chip, to see if there are any low-hanging fruit we might be able to fix common mistakes that students make all the time. Anyway, so I'll take a second to demo some of these because they're fun. Am I doing okay on time, Cam? Are we?
Yeah, you're good.
Okay, just let me know if you want me to speed up or slow down.
Yeah.
Or...
As I mentioned, some of these can go for 5 hours.
Okay.
You're doing great.
All right, so what I had the students do was basically come up with a fun video game. Again, this is teaching them how to ride the bicycle, so to speak, where they're just trying to get the knack of how to keep their balance in programming. A lot of them, this is the very first time they've really dug into programming. And so again, I think Spin 2 is a great language for this, understanding kind of what's going on in the hardware. And on these video games in particular, the parallel processing really makes things nice, because a lot of times in video games, you want to pause something at a speed that's much slower than the computer speed, but more at a human level speed, where you want something to pause for half a second or so. If you're running just everything in a main loop and the whole loop just kind of stops at that position, that becomes a mess. Or you have to start, I don't know what the right term is, kind of like multiplexing, where you've got time increments in for loops that are doing certain things at certain intervals. So that just becomes a headache. So it's really beautiful to be able to make graphics and stuff happen at different times on with different parallel processors. So this is another great way to get them to understand parallel processing, is to have them work on a video game like this. So as you can see, they're using a lot of the debug stuff. And without further ado, I'll just run this. I've got this running now on a board. It's got an analog potentiometer that's hooked up outputting analog voltage using Johnny Mac's code to be able to read in that value. And then it's got buttons for the various things you might want to do in a video game. So this is running off the P2. Also, this is showing you that right now there's nothing in the RAM because it's running the default Flash program. Again, that's the safety feature to make all the pins in input safe mode except for those two. All right, so I'm going to download this, and this one is called Book It to the Bank. And so you've got, unfortunately, we didn't have a whole lot of graphics, so we're just using the ASCII characters, ANSI characters. But you're the $sign, and you're jumping around, and you've got a laser. And there's logs you have to jump over. And I spilled my coffee and I was late to the mic. So this is the debug in action. They've got some extra terminals to show the score and the lives left. Kind of fun.
Wow, you were able to make a whole video game using debug, huh?
Yep. So
that's funny.
So I had 87 students each make a video game like this. And I think they had a lot of fun with this by the end. They really dug into this. And again, this is kind of giving them the knack of how to program in general. So all these skills could then be implemented on more mechatronic things later on in the semester. So yeah, the graphics left a little bit to be desired, but they were drawing all the things in shapes and stuff. And so here's another example. We've got a missile defense type game. So you're the ball and turret, and you're trying to shoot down these missiles coming in. So really fun. I mean, this is, they had a limit. They couldn't write more than 300 lines of code for this. And I gave them a lot to start with. Spaces and stuff didn't count. They did some old school Atari games. This is a fishing game some of you might have played back in the early 80s. So basically you have to catch the fish, and there's a shark at the top that tries to eat the fish if you catch it. So it'll eat the fish.
Get him, Gavin.
Yeah. This is like real life fishing, I guess, for me. All right, so that's another example. Here's more of a Space Invaders style game. This one has a start screen. That's kind of cool. So it's using the potentiometer to decide if you want to play. I can't remember what happens if you say no. All right. It says, wake up, sheeple. I used to say that people that were using Arduino were sheeple and there's following instead of leading. All right. Here we go. So we got these little Space Invader things. You can shoot lasers. It's got the score and the lives and levels going up. So this is another example. We have a recreation of Pong. I'm actually playing both players right now. This one doesn't have AI. So, all right, so that's Pong. We even had Frogger. Every level it gets a little bit harder, more lanes to get across. And one student even went so far as to, oh, I didn't get the, let me find another one.
I think we need to add some kind of polygon type into debug.
Yeah, polygon will help. Another thing I was going to get to is sprites. So actually, I messed around with this because I've used the game Duino, which is something that I forget who developed it. There have been a couple iterations. I think now they're using an FTDI Eve graphics processing chip for the later iterations. But the original was an FPGA, and I think the person who developed the Propeller Arduino Shield compatible board spent some time working on that in assembly, and I was able to fix some of that and bring it in. And so actually I had the game Duino 1 running on a VGA monitor with great success with the students. So actually I tried this and I had a student for extra credit work on this. And so what I did was I worked out the sprites as bitmaps essentially. So these are actual 16 by 16 pixel images, and each of these bytes references a color palette to, this is Mario's head. You can kind of see the top of his head and the bottom of his body. So, and then I wrote a really quick way to look these up, probably not very efficient, to be able to draw these as dots on the plot screen. So this can actually create kind of a Nintendo style game. So it's a little bit slow right now, but you can actually see it's drawing 16 by 16 sprites to be able to make the Goombas and these little brick platforms or sprites as well, and the fireballs. So this would be kind of fun. Kind of a rabbit hole we might go down, but I think programming video games is a wonderful way to teach students how to kind of get the knack of programming. So I think there's something here.
Agreed. Yeah, that's neat. Well, we could make a little primitive where you just upload a sprite definition and then you can place it, and it will just draw it for you.
Yeah, I think so. A couple little tweaks might really help. I know there was a discussion on one of these forums a couple weeks ago about being able to have input to the debuggers, and I realized that would cause timing issues, but that might be nice too, not to have to. So I actually use the PST a lot in various applications because we needed to be able to enter values. So so we had to use the parallax serial terminal to be able to have data going both ways from a keyboard on the PC into the Propeller 2 chip. So I think some way to do that would be nice, even if yeah, I know that's tricky because they're all sharing the same UART.
Yeah, well, you know, if we had a P2 acting as host, it could be no slower than one-way communication because we could respond, but the latency on a PC is so high. That's the problem. Right.
Anyway, there's a lot of cool ways we can go with this. There's another student that did Tetris. I could try to dig that up, but you could probably get the idea. All right, any questions about the video games? And this was, again, a great way for the students to kind of explore programming on their own terms. And they all worked out various code and really got the knack of Spin 2 programming in the process. All right. So then the next lab got into pulse width modulation and motor control, staples of mechatronics. We look at PWM as a form of digital analog conversion and the primary way that we control the speed of brush motors. And I took the time to dig into how they configure smart pins for this. I think that PWM is so fundamental to mechatronics. I really wanted them to pop the hood and actually fully understand what they were doing. So we talked about the sawtooth PWM generator smart pin mode, and they understood how to manipulate those bits to make that happen. Is a quick demo of how that worked. They use a 3 LED module, I guess you'd call it, non-addressable. So basically you send in the PWM signals to the red, green, and blue, and they change their shade, and you get any color of the rainbow you want. So they're doing this from scratch with the smart pin setup. Actually, this bit me, I didn't notice at the time, but there's, just in case somebody else makes this mistake, there's signed and unsigned modular commands in Spin too. So you want a plus double slash most of the time. I did this back in March.
Those pins could probably be started at the same time if they're given the same configuration.
In one command? So basically just make this 3 bits instead?
You'd say, if red, green, and blue are consecutive, then you could say red, add pins 2, and if the other information is the same, it'll just assign all 3 pins at once.
This is one of the places where I come in, because I've taught over 1,000 students at this point, and I understand how confusing it is for the first pin. So that's brilliant, and it would be definitely the right way to do it. But sometimes the right way to teach it isn't the right way to implement. Right. So that's one of my problems. Is I have to really step back and try to think about the first time somebody sees this. What is it? What are they gonna do? And I've seen so many people crash and burn that I've come to start to understand how to tweak things just right, so that people right off the bat can appreciate it. So yes, you can make this more efficient, but not in terms of the education, right, and the learning curve. So, but that's cool to know. Yeah. Yep. So we dig into setting up the pins and setting the duty cycles, and then we get into H bridges. I found a nice inexpensive H bridge chip to use. It's a Texas Instrument, I believe. There's some other nice ones. Plolu does a great job of doing breakout boards for these, but this is the DRV8833 chip, and I was able to get these from Amazon. There's a lot of variation in the various vendors that had these, so some of them have different colored PCB boards and stuff, but they all seem to work okay. So it's nice. It's a dual H bridge, originally designed for bipolar stepper motor control, but it's nice for robots with 2 brush motors as their wheels. And it also just ran off of 5 volts, which was nice. All right, so then at the end of this, then we got into quadrant encoders and how to use the smart pin mode to read those, which is also incredibly useful for mechatronics. Just another great example of why the Propeller 2 is perfect for mechatronic applications. Just being able to effortlessly handle quadrature decoding without having to have a separate cog dedicated to it. So that said, I did kind of show them how it would work in code just so they can understand the process of what's happening. So I kind of showed them what would happen in Scratch. They didn't actually run this, but just to show them how it's just doing a case, and it happens to be at this position, and then from here it's going to change, and then it's either gone counterclockwise 1 or clockwise. So they kind of understand, conceptually what works, but then they use the smart pins to do it. And we used one of these just cheap, I think 16 count quadrature encoder systems. But then they did a project at the end where they used the next version of this. So I had this little 3D printed mount for the cheap gearhead motors. And so now they have 2 Aire distance sensors that are slightly offset, so that with the single track, they can measure a quadrature output on 2 channels. And so they're able to use the smart pin quadrature mode to be able to turn this into basically a servo system from scratch. So they basically build a RC servo motor from scratch with proportional control. So if they have an output position they want it to be at, so like let's say they want it to be pointing this way, but it's actually pointing straight up right now. Because that's a ways away, they might actually, from the proportional control, determine what the error is and decide that is enough. They want to go full 100% duty cycle to push the motor that way. But then if they're really close to where their target is, they might just want to tap it with a very small percentage duty cycle. So this is exactly how RC servo motors work. So doing that from scratch, I can show you videos of some of the solutions that they've done for these. Yeah, let me show you that. So because this was all done remotely this semester, when the students had a deliverable for something like this project, they would make a video of it in most cases. So here it is showing this motor kind of making stepping motions to various positions. The positions are displayed on this debug terminal in blue. So it's basically making incremental positions, again, kind of like an antique Geneva drive, but in this case, getting feedback from the quadrant encoder and setting various target positions in the Spin2 code. But again, it's adjusting the duty cycle based on the error of how far away it is from the target position. And it's reading these, the feedback from the homemade quadrant encoder system, which is again, just reflecting light off of the mirrored encoder disk. All right, that's the next one.
Okay, quick question.
Yes.
On those video games you saw where you were doing the pixels, were you using bitmaps or plot?
We were using plot. I tried to get bitmap to work, but we needed to combine displaying text and shapes. So with the plot, we were able to display text and shapes when we needed to.
Right. Okay.
And then for, again, when I did what the sprites are essentially like bitmaps, but it was basically drawing dots instead. So it was just, that was very time consuming to do 16 by 16 sprites.
Okay.
But yeah, I think there's something there, and I think particularly in education, you know, kids just eat up the idea of they're making video games. That's a lot of fun. So, and it's again a great way to learn programming. And again, it's exactly how I learned programming when I could mess around in math class, programming games into my TI calculator. So, I'm sure there's lots of academic journal papers that people have written about how great it is to teach computer science through video games.
Well, you know what's great about what you're doing is you're dealing with people who are just coming at all this stuff fresh. They don't have all these preconceived notions from computer science. So they're able to actually just do stuff without getting hung up on all kinds of formalities and constructs that maybe aren't needful.
And I think that's really important, particularly for any teachers out there in the K through 12 area, that I think at that level, it doesn't matter what language it is. It really is just more of the structure and what you can do with it and how to make things exciting. I had a lower school teacher back in the 1980s who was really brilliant because she had us using, I think, Apple II GSs with a game they called Logo, where you had this little turtle and you basically would draw things, but you'd make it rotate and then draw a line in a certain color. And it's just that was so awesome back in like 4th grade to be understanding how computers are changing everything and how to talk to them. I'm sure everybody has a similar story to something like that, where they just kind of woke up to just how neat computers are. So I think that's really the trick, is we want to get, you know, particularly K through 12 students kind of hooked. So they want to do things on their own. And that's the video game's great because it's just, it becomes fun. And it really is a wonderful platform where they have the agency to make whatever they want, whatever they can come up with. And so they set their own goals. So they'll say, like, well, wouldn't it be cool if my spaceship could do this? And then they're going to stay up all night trying to get their spaceship to do that. So they're making it go in the direction they want it to. All right, speaking of making things go in directions, we studied RC servo motors. Again, we dug into how they actually work, because a lot of times the students are making these from scratch. And again, we kind of do that in that little project I showed you with the homemade servo motor systems. I did talk about continuous rotation servos and why they don't want to use those now that they understand how to control H bridges and do everything on their own. So I think those are nice, but I always have students in their capstone projects in their 4th year come up to me saying, like, well, this, you know, RC servo motors just told us can only go 90 degrees or 180 degrees, but I just found these continuous rotation motors. So these must be awesome because they can go, but they don't understand how they work. All right, they designed a little system where they try to pretend that they're working in an automated manufacturing system where they need to draw a logo with a spray paint gun. So I tell them they have to make this motion profile. So they're changing the speed of the RC servo, pretending the spray paint nozzle is kind of painting this logo as the part goes over above it. And I've got some examples of what that looks like. So this is their deliverable for this project. So they basically have to have a start button that starts the motion. And then they also have to incorporate a kill switch. So if anything goes wrong, somebody gets their hand caught in the machine, it can automatically unwind itself. And so for this, parallel processing is really nice because you can dedicate, rather than having to deal with interrupts, just say, okay, if anything bad happens, somebody hits the kill switch, immediately stop it, unwind it, go to the safe position and wait for a restart. So that's another thing that I think Mechatronics brings to light that is a great reason why you might want to program in assembly or have parallel processors, is that you know, on a Windows PC, if you get a blue screen, it's usually not the end of the world. But if you're designing a system like for a car airbag system, and all of a sudden when the car's crashing into a wall at 80 miles an hour, there's a little blue screen and it glitches up, that's a big problem. So sometimes you just want to have code that's so reliable and robust, you know, that you can actually talk on the metal to the computer in assembly, just because it's only a couple lines of code, but it's so important that nothing goes wrong through some kind of a compiler middleman. It makes a lot of sense for us mechanical engineers and mechatronics to actually dig down into assembly and be able to have full control over the system. So I think that's an important aspect that, again, separates us from typical computer science applications. You know, that's one of the reasons why just having really elegant code makes sense. And so, in case it hasn't been expressed before, one of the beautiful things about this chip and the fact that the chip has made this so easy to program in assembly is that a lot of the people in this community are going to be writing code that is just perfectly beautiful and written at the level that this controller understands. And all we have to do is tap into the objects that they've written, and we can instantly just do things on this little inexpensive chip that are, you know, stuff that you normally wouldn't be able to do on a chip of this cost. So, you know, things like the HDMI output or floating points or other things that it can do kind of effortlessly for us is really just night and day compared to the piles and piles of junk that people have written for Arduinos and other computer systems. You know, and again, everybody's dealt with, you know, blue screens of death on Windows to kind of understand what happens when you just have bloat upon bloat of, you know, shoddy code. And again, in most cases on a PC, that's not the end of the world, but in mechatronics applications where it could be life or death, that's a big deal. So, all right, so that's this RC servo demonstration. You know, again, this is the bread and butter of mechatronics, making things move. And then I'll talk about the stepper project in a second. Actually, I'll just show it off here. So I'm teaching them how to program stepper motors. We use 6 lead steppers because then we could program as both, you could use them as both unipolar stepper motors and just have them run through a Darlington transistor array with the current going in one direction. But then as another project at the end, we used a bipolar stepper motor mode. We just used 4 wires and we were able to use a microstepper driver chip. That's this last one is an exam that I had them do. I'll talk about that in a second. All right, any questions about motor control and what we've done here? So again, all this stuff is going to be in this Exploring Mechatronics textbook. So, you know, kind of the go-to reference for how to, you know, quickly get steppers and servos and how to do, and the in-depth kind of background in terms of why they work the way they do. I know that that John's already done some quick bites and stuff to get people started, but I'm hoping this will be kind of a more formal kind of textbook-like approach to kind of how these work and why you'd want to use them. All right, so that's what you just saw in the video. All right, then we get into some various communication protocols. So I'm gonna be working out tables like this to kind of help people as a reference kind of see what the pros and cons of the various, in this case, digital communication protocols are. I also have a similar one for, you know, steppers versus servos versus, you know, quadrant encoder based servos or absolute encoder based servos. So just kind of go to references that help people understand applications and which one they might want to go to and why. All right, so again, all this is coming. I used a digital potentiometer chip in my labs, and it taught them the basics of how serial peripheral interface works. And of course, they're rolling that from scratch with spin code. And then I was able to use the logic analyzer debug mode to great effect here too. So again, one of the biggest things I was worried about is not having oscilloscopes as I sent out these kits to everybody, but this actually worked well. They're able to see the SPI bus and see the data being transmitted, in this case, from the P2 to the digital potentiometer chip. So this worked really well. Again, I think if we could polish this a little bit and make it kind of like the Cyberscope interface or just some easier ways to tweak the ranges and triggers and stuff, I think this really would be a game changer. All right, and then I had them build basically a successive approximation analog to digital converter from scratch. They basically hooked in an op-amp comparator and they generated a analog output voltage, in this case, just using the digipot, not fast, not something you really want to use, but it kind of got them thinking about how to build an analog to digital converter. And then that led us into using the smart pin and the Delta Sigma ADC modes. I just used a nice little, yep.
one guy who's been on here said that he was using the level comparator mode, which is in the smart pins, to do successive approximation. And he was getting way beyond the bandwidth of what we're getting out of the Delta Sigma ADC.
Interesting. How many bits? Is that 8? Those are 8-bit?
It's 8 bits. Yeah, it's only
okay.
8. You know what? It's really like probably 7 really good bits.
Cool. Yeah, that'd be interesting to incorporate into the book. Yeah, that's a neat idea. And is he using a comparator smart pin too?
Yeah, he was using the low-level configuration of like a 8-bit level compared to the pin.
So it's basically just using 2 pins. So one smart pin in DAC.
Just 1 pin.
One pin in a level comparator.
Yes. Yeah, the last of the modes, if you look at the mode chart for the low-level pins, the last couple are where you compare an incoming pin to an internal 8-bit DAC.
Cool.
And I just made
what was the bandwidth he was getting off of it?
I think he said something like it was over 10 megahertz. I want to say 20.
Oh, wow. Oh, cool. Okay. Yeah, I'll have to check that out. That's going to be cool. Because particularly for oscilloscope mode, that would be pretty neat. Awesome.
Yeah, the trouble is with our normal ADC, the analog front end limits you to maybe 2 or 3 megahertz before it starts to attenuate.
Got it. I'm gonna bring up the Google Doc of this so I can show the GIF of this, because it's kind of this is basically what we're talking about. For everyone else, the ability to have oscilloscope capability built into this P2 chip is pretty phenomenal. Before this, the best game in town, at least a couple years ago, was Digilent. Had this wonderful analog scope. They teamed up with Analog Devices and Texas Instruments, some others, and it was just beautiful. And they kind of subsidized the cost so that students could buy it for about $100. And but then National Instruments bought them out, and then they upped the price to like $300. It's just kind of crazy. This is the Google Doc version, and so this shows a GIF of this in action. So we had a little Aire distance sensor, and we basically had the analog mode coming out of it, so an analog voltage coming out as you move your finger over top of it, and this actually shows you kind of a real-time oscilloscope view of it. So again, this really helps the students to visualize what's going on.
Cool.
All right, so then I've got, I did a final exam for the students where they basically had to use their kit. So it wasn't just a written exam. They had to, actually to build a system. And so I picked a garage door because I thought that was something they were all familiar with. And so what they did for that was have to use the Propeller 2. They had a 4 relay module to work with. So I basically gave them a bunch of parts to work with, a bunch of components, an IR distance sensor, and they basically had to come up with a system where there was a remote control they'd push just like a garage door, and then the IR distance sensor was like a safety beam, so that if a dog or a cat ran underneath or a kid or something, it would automatically stop the door and go back up. So they had to kind of pretend that the DC brush motor was hooked up to a garage door, pulley or whatever system they were using to chain. But they'll walk you through the solutions here. So this is just a great example of how they were able to actually apply all this stuff as an exam, write the Spin 2 code, and put it all together. And of course, really understand an H-bridge. The idea was they were going to use the 4 relays as a simple H-bridge. Some of them were clever enough to figure out they could do it with 2 double pull, double through relays. So they're basically building a garage door system completely from scratch. And this was a they weren't allowed to use the internet on this, so they weren't allowed to just Google kind of how to do this. That's one of the things I've really enjoyed about the Propeller 1 and Propeller 2 is that, because it's not quite as mainstream as the Arduino, particularly with the most recent generations of students, they just are in this sort of monkey see, monkey do mentality, where, really having to pry them away from that, where all the answers are already online, all they have to do is look them up, and actually have them start to think for themselves, and become competent to tackle things from a fresh perspective, and not just kind of follow what everybody else has done. I think that this is really neat, and this is something that I think that Parallax has done well. All right, so that was their final exam, and then as a final project, they had to I basically, as I mentioned, what I wanted to do was a PID-based hoverboard type inverted pendulum robot, but I ran out of time, and the yellow motors just weren't quite up to the torque I needed to be able to push these boards around. So what I had them do instead, and I guess it's kind of a good in summary, is I had them pick an antique mechanism, and I pointed them towards a neat website for any of you guys who are into this, but they basically took this old book, 507 Mechanical Movements, and they animated a lot of these online. So you can basically go through the 507 different movements, and a lot of these are just come to life, and you can kind of see kind of how they used to design things. Again, the old days of mechanical engineering, when you had to come up with really clever shapes to convert continuous rotation motions into more useful motions. So what the students had to do was pick one of their favorites of these. There are all kinds of YouTube videos and stuff as well that show these, and then come up with some kind of an application as to why, what the certain application was for wherever this antique mechanism was, and then come up with a modern mechatronic equivalent. So I have to say, okay, well, instead of using this interesting way to convert change of direction, I can do it instead with the unipolar stepper or an H-bridge or something. So they basically took all these antique mechanisms, all 87 students in my class, and converted those into some kind of a modern mechatronic equivalent. All right, are there any questions about what we did this semester and where we're going with the P2-based mechatronics textbook and kit?
We have some other professors here, and I'm curious who teach mechatronics, what they think, because some of them are just getting into the P2, and they'll probably want to use some of this material. But is anybody else using the P2 yet in university level?
So I would say if you've used the P1, jumping into the P2 is not that big of a deal. One thing I've actually been working on, and I'm sorry this hasn't been brought to the public yet. I think there was a forum post with something similar, but this is actually something I worked out for the P1 for Spin 1 versus Arduino C. And so I've added the Spin 2 to it. There's a couple things I need to fix, and maybe I'll get Chip or Roy if he's willing to help out with this, just to kind of double check, or anybody else that's really familiar with C. Kind of show this juxtaposition of kind of, if you're familiar with C, this is how you go from that to Spin 2, or if you're familiar with Spin 1, this is how you go to Spin 2. This is what's different and what's been improved. So this will be released soon, I hope. And it's just sort of like, I call it the Rosetta Stone. It's basically just a way to be able to translate back and forth between these languages.
Between Arduino, Spin 1, and Spin 2.
Yep. So if anybody doesn't know, the way that the Propeller 2 does random numbers is really, really cool. So that alone should sell a computer scientist on this chip.
And in your class, are you having them go as far as doing any lasering or much 3D printing for their final projects?
So there's 2 or 3 classes. There's a couple. So for the mechatronics course, this is a survey course in teaching them the basics of robotics. So they're understanding things like PWM and servos and steppers and ADC, the fundamentals of kind of how they make modern mechanism machines. And then in the capstone design, which is sort of a more fun course where this is kind of their victory lap after they got into their 4th year, their senior year, where they're supposed to take all of the stuff they've studied, fluid dynamics, strength materials, statics, thermodynamics, mechatronics, and bring it all together to actually make machines. And so these typically have pretty decent budgets where they can spend, a couple $1,000s on building something like a jet ski kayak or a robot that's made out of metal, or things that are kinetic art clock. And that's more of where they have a lot more control over the design. And that's also a learning experience though too. So it's not always, I always have to tell them the deliverable of the capstone course isn't so much the product or prototype they've come up with at the end, is that they've grown as engineers in that process. So they really are the deliverable, and their education is the most important thing. Because of that, a lot of projects don't actually make it to the finish line, just because I think if you make them too simple, so that's very obviously all of them are going to finish, you're doing something wrong, you're not pushing them hard enough. Obviously you make things way too difficult so nothing ever gets finished, that's not good either. But finding that right balance where it's just, it's difficult enough that if they grow and they push themselves and rise to the occasion, they can make it. So that's the trick. But I've got a lot of projects, that got really close and just kind of heartbreaking. They're not quite finished. I might use some time this sabbatical to try to wrap up some of those kinetic art clocks. And there's a UVA themed pinball machine we worked on a couple of years ago based off of Propeller 1 that didn't quite get finished. Really cool.
So how about this? Since you've been teaching for so many years and companies like Parallax have put so much energy into teaching teachers who teach students, are you seeing the capability increase now over just say the past 10 years of the incoming, let's say freshman, sophomore who's been through high school? Have they been exposed to any of this in high school, which makes them more capable now in university than they used to be?
Yeah, so honestly, it's mixed. There's no question that the generations of the last couple of years have been incredibly good at multitasking and absorbing a much broader array of things. So they really are doing so many things at once, through the internet, and they're able to absorb so much breadth at once. But I think a lot of the depth is lost, and also a lot of the creativity has kind of diminished because of the fact that, again, everything is already online. So anytime they want to build something, they just go to YouTube and see what somebody else built, and they want to do the same thing. One of the things I force my capstone students to do for their senior designs is they're not allowed to do something they've already found on the internet or somebody else has done. It has to be unique in some way. So it can't just be kind of a copy paste from instructable.com. This is the Arduino code. Look, I've got an inverted pendulum. It's got to be something that's kind of uniquely theirs.
So they have this high level thinking, but not the low level building blocks sometimes.
Yeah, the high level thinking and the ability to integrate almost to a fault, where it's just the fake it till you make it has become like professional grade, where it's just they're so good at just copying and paste Arduino code and other things and just being able to kind of get it to work even though they don't understand why it works. Unfortunately, a lot of times the kind of house of card tumbles in their design courses where they've just relied on so many other libraries and stuff that once something doesn't work, they have no idea why it doesn't work, and then they're just kind of lost. So even though it's a lot more tedious and requires a lot more energy to build things up from the ground up, at least they have full agency over everything they've done. And again, that's really where the Propeller 1 and Propeller 2 chips shine, is being able to really pop the hood and see everything when you need to. That really is, it's really great when something doesn't work, you can actually go down and understand everything. Nothing's hidden.
Other questions for Gavin here?
Hey, Gavin, I got a question for you. You got a lot of energy, by the way. I think I'm going to have to take a nap after this. But your curriculum is for mechanical engineers. Do your double E's see the Propeller in their studies?
The double E's study the MSP 430 by Texas Instrument. There's my doppelganger in our electrical engineering department has kind of paired up with TI to great success. I can't blame them for that. They're pretty big in the field, but they use the MSP 430. I think some of them might occasionally use the MSP 432, which has floating point hardware in it. But they have to deal with the embedded systems from a different angle. So they're not really so much interested in motor control and being able to manipulate things in a robotics sense. So that's really the mechanical engineering domain. So they're more interested in signal processing and power consumption and noise filtering. So it's but there's no question that mechatronics is where these different worlds merge. And so one of the things I found that's important within teaching mechatronics is to not let the different disciplines become siloed. So I think if you're designing something from a mechatronics perspective, you need to be able to see things from the different angles, from what you can solve in electrical engineering versus mechanical engineering versus software. I joked and said about the disabling the F11 key so students couldn't overwrite the EEPROM on the P1s or the flash on the P2 as being a problem. So we need to solve this. So there's a computer science way to solve it, where you actually go into the x86 code and try to figure out where to disable the F11 key function. That's one way to go at it. You could also come up with an electrical engineering solution where you actually hack into the keyboard and throw a chip in or something to or snip the wire for it. Or there's the mechanical engineering solution, which is just pop the plastic keycap off and stick something in there so it can actually mechanically push. So there's 3 different ways to solve the same problem. And so a lot of these devices need to be thought of from those 3 different angles, because sometimes when you need to replace an antique mechanism, or if you need to make a motion, like have it start, move 90 degrees, stop, you could go at it purely mechanically. Obviously in this day and age, that's not the right way to go about it. You could add a stepper motor. So really being able to understand the pros and cons as you juggle these 3 different disciplines is important, and that involves a bit of depth and breadth.
Yeah. I guess the first semester for those guys doing the TI or config files and IDE, how complex that could be. And I got another question. Did you have pushback from the school board or your colleagues when you went from Arduino to the Prop back in, I guess it was 08, you said?
That was from the BacicStamp too.
Oh,
okay.
Actually,
we were using some of the later versions of BacicStamp, the PX and others. But so no, not really. We have a lot of agency in the college level. I know at the K through 12 level, there's a lot of metrics and constraints. Within engineering at college level, we have what's called ABET, the Accreditation Bureau of Engineering and Technology. So every couple of years, we've got to go under a review. So most American engineering university programs are ABET accredited, is called, but they're not too meticulous, or they don't go into too many details of exactly what you're covering in terms of microcontrollers, or concept based.
And then my final question, since the COVID started, some colleges have adapted, or they were forced to virtualize their curriculum, and some adapted and actually made their business plan more virtualized to capture more students worldwide. What do you see, if you had to do this in the future, continue this virtual lab, what would be your idea of the hardware that you send out? Something similar to what you got, or yeah?
So yeah, so I had the budget, and I thought I had the time. I didn't realize, I underestimated how long this would take. But I made these a little nicer than I probably should have. But I figured if I was going to make them right, I was going to make them last for 10 or 20 years. And they're modular, so they can be replaced. We can upgrade to the latest version of the P2 Edge and stuff very easily. I mean, this easily. So it's pretty convenient. But
and were the students actually, was it value added for them working from home on a Zoom meeting?
I think so. I think across the board, to be completely honest, a lot of students were furious that they're paying full college tuition for this sort of virtual experience. Because honestly, I've come to realize that most of what happens in college and what changes people over those 4 years is not happening in the classroom. It's the environment. And so, our university at the University of Virginia is a great example. We've just got so many outlets and extracurricular clubs and ways the students can socialize and grow, that it's really not just the classes. So there was this huge threat, I guess, 8 or 10 years ago, of the massive online open courseware, the MOOCs, and how those were going to revolutionize colleges and how nobody's going to want to go to schools anymore. And it was the exact opposite has happened, where people have realized that it's the college experience that the students treasure, and that's most important. And so that's really, obviously COVID threw a huge wrench in that. We've all done the best that we could. And I think that it's, we're getting through it, it seems. I think most universities in the United States, at least, are going to be opening up and back to normal this fall. I'm on the faculty senate of the University of Virginia, so I've got some insider info in terms of where we're going with that. Some universities have even gone so far as to mandate that all students and faculty and staff coming back have to get vaccinated. We haven't done that yet, but I think that's something, I think people are pushing hard to get things back to normal, at least in the US. I think in terms of the educational value, once hopefully everything is back to normal next spring when I have to teach this survey course again, I'm still going to be sending these kits out to every single student. I think that this is definitely the way to learn it. The trick is if we can get this down to the right price point. So in this day and age, a decent textbook is usually around $200 US, which is very expensive. So if we can get it down to that price range, though, it's not unheard of to have every college student buy their own $200 kit or $200 to $300 kit and be able to keep this after the course is done. There's obviously logistics in terms of how to get these back, how to make sure everything still works on them, how to test them, get them all cleaned up and ready for service again, particularly when it comes to the parts we use. I didn't actually get into that, but this is.
I'll make a comment on that too. So what Gavin's doing is really opposite of what many professors do, right? Students have to buy $200 books, and this is how they get promoted, how they get tenured, and how they get recognized. And what's really best is to give students hardware with something free. And that's what they'd rather have. So I really commend you for that and thinking this way. And I had a question too, maybe you can comment one more time, is what Kevin Arndt was talking about, I believe. So I answer the educator hotline at Parallax. It's mostly high school teachers. This last year, they've done two things. They've sent hardware home or they've done nothing. So a lot of classes are returning now, and they have robots that were literally left wired on a desk and in some state of, wherever they were in a tutorial. Now that you've sent hardware home, and in prior years you were having them go to lab, have you viewed their uptake and their progress and their interest higher, like all those variables?
Yes.
Would you say?
One of the, I hate grading so much that one of the things I've done at the end of the course for the last many years is to actually interview the students. And so a silver lining of the pandemic for me was that this year I interviewed them via Zoom. So I didn't actually catch all the strep throat and colds and whatever they normally have. So normally it'd be, a week or two of interviewing each student for about 10 minutes in my office, side by side. So that was just a nice thing about that, was virtualizing that was safer for me. But it's been night and day in terms of how few students were left behind out of this giant, massive, safari I was taking these 87 students on. That most of them, the grades were higher than they've ever been before, and I wasn't changing the curves around. It was because they really had absorbed the stuff at the individual level more. Because of the way I had this set up for the previous years, there were 7 workstations within that Mechatronics lab I showed you at the beginning, where the students would sit down, work on a board in groups of 3. So it was really 3 people sharing one computer, one breadboard, one kit of parts. And they had 2 hours to finish the lab before the next group would come in. And we just did sort of assembly line cookie cutter procedure. So it's just been night and day, both in terms of how much they've learned, but also how much time they've had with the hardware themselves. So I think this is really the way to do it. Again, there's a bit more cost and logistics involved. And whether or not this is going to be kind of like one-time use, so we don't worry about trying to return them and sort through them and repair things, and they just buy it right out and it's theirs to keep for the rest of their lives. I think if we can, again, incorporate multimeters and oscilloscopes into this chip, that really makes it worth it. And it's stuff that they'll use beyond just the course. But finding that price point and figuring out exactly how this is going to make the most sense is something we need to work on this summer. But I'm looking forward to the challenge.
Great. Any more for Gavin?
Kevin, I got one more question. My local area, Google subsidized the rollout of Chromebooks for the grade schools. So that's what the students are using here. So have you ever had a student walk into your classroom, university level student, with a Chromebook to do engineering?
I have not. I'm not familiar with it. Can they run x87 native, or are they running ARMS? What are they?
No, well, it's all cloud-based. It's all cloud. You can't load a driver for even a USB. It's very limited. And within that, the internet at schools are very, you can only access a few sites. So they're basically getting their lesson plan and typing on, on their local drive. I don't know what they're using it with, but it's very restrictive in that initial learning of Windows or even a Mac. And then you go into the university setting with a Chromebook background. I don't see how they got to learn Windows.
Right. So to me, you can get single board Windows computers for the same price as a Chromebook.
Yeah.
I guess without the cloud, they wouldn't be quite as powerful. For the engineering students, they need to use CAD. So a program like SolidWorks or Inventor, that's just going to be gigabytes of RAM, and that's a big task that you usually need at least a $1,000 roughly computer to be able to run those efficiently. The Latte Pandas, and there's some other ones you can find on Amazon for around $100 to $150. They work fine for the Propeller tool. And again, as Chip was saying, if we can figure out some way to actually have built-in way to program these, that would be very interesting. Most people have smartphones and stuff too, or tablets, Chips. So maybe there's a way to have an Android app or something, Apple app that programs these?
Well, one of the programming methods that's been under discussion is totally browser-based.
Yeah. And that's Blockly does that right now. BlocklyProp is probably, yeah.
Nobody could say it. BlocklyProp. Well, Gavin, you have a heck of a lot of energy, and I hope it infects some of the other professors here. There's several watching. Actually, one of my favorites is Frank Nichols, who wrote this book, who has been using Parallax for 20 years, and he's taught all around the world. And he's actually now starting to use the P2 too. So I know this will inspire him and several others. So
thank you, Ken. Thank you.
Yeah. Thanks for joining us too.
Yeah, I'd like to say, Gavin, fantastic presentation, really inspiring. Thank you very much. And when is your book going to be available?
So we're aiming for the end of the summer. So ideally in time for anybody who wants to try to use it this fall. So I tried to kill two birds with one stone. This semester I went all in, ported everything over the P2 and really got a lot of kind of feedback from the students and pushed myself to really kind of jump on the burner and get started on this stuff. So I think I've got a really good first step into this. It's just a bit of polishing and working out the bill of materials. I didn't really get into the parts list that we use, but this is something that we're working closely with Ken on, and the rest of the Parallax team is trying to come up with a set of the components that make sense in terms of the price point and what we need to cover. So these are just some of the things that I shipped out to the kits this semester. So we'll be building upon this. So once we get more of the details worked out.
Yeah, okay, buy a copy. Thank you very much.
Absolutely.
Great, okay. Unless there's anything else, we'll let Gavin go. I think his semester just ended like yesterday.
Yeah, I got my grades in yesterday, yes.
So are you totally worn out? You must need a break, right?
That's what the sabbatical's for. So I'm looking forward. I've got work to do this summer, but I get to focus on working on this book. And there's a couple other things I promised to do, but not all of them are things I don't want to do.
So the sabbatical goes until winter semester quarter?
Yeah, technically it's until December. I've got to tell everybody what I did to deserve not having to teach next fall. But one of the things I've got on my docket, we've got a beautiful state-of-the-art flight simulator that's actually got actuators, so it's like a roller coaster when you're inside of it. So I'm going to be upgrading that, hopefully getting Microsoft Flight Simulator 2020 to work on that. I'm hoping to wrap up my private pilot's license training too this summer, and so that's fun. There's some other things I've promised to do.
And what instrument do you play?
In music, I play a lot of things. One of the benefits of declaring a music major in college was that you got lessons in whatever you wanted, kind of as part of your tuition. So I took piano lessons, guitar lessons, operatic voice singing, even pipe organ lessons. So that was kind of cool. Actually, because nobody really used it in a while, I was actually up in the rafters retuning the pipe organ, kind of adjusting the pieces of lead over top of the pipes. And it's a neat instrument. So I play a lot of instruments poorly. I play the piano pretty well. I'm working on trying to get through the third movement of Beethoven's Moonlight Sonata at the moment.
Very neat. Well, we'll give you a break, and then Stephanie's ready to go. She already messaged me. Can't wait. She recognizes all those parts in that bill of materials already.
I've started working on a Google Doc, so I'll share that with you, Stephanie and Ken.
And yeah, that's really our first order, is to get that figured out so you could revise material.
Yep.
Chip?
Thank you so much for being here. This has been really fun to see.
Yep.
I've really enjoyed your presentation.
Awesome. Well, thank you all for the support that you guys have been creating throughout the last couple of months or years, even on this P2 development. It's really been a wonderful tool for us to use. And I'm just excited for all the possibilities in the future. So,
yeah, you get me excited about things.
Me too. And if there are any other engineering mechatronic professors out there who want to sample this, I'll gladly send you a kit, as I mentioned in newsletters before. So just send me an email, kgracie@parallax.com. Thank you so much, Gavin.
Absolutely.
Okay, yeah, the clapping, I see it happening.
Thanks all.
All right, well, we can move into the informal side of things. That was informal, but now we get really informal with some limits on whatever we want to discuss, I guess. So anyone who wants to hang around, please do. Any topics of interest to people? If James, oh, he signed off, okay.
No,
Steven?
I'm here, I think.
Yeah, did you want to show what you...
Yeah,
okay.
I do actually. It might be relevant to some of these things we've been talking about.
Yeah, because I figure we're keeping you up late too as well, aren't we?
It's only 12:15. Let me see if I can make this work. I'll put it into a PowerPoint presentation instead, so maybe I can find the screen this time when I share it. Let's see if I can find it. Is it better? Can you see something yet?
Yeah, it works.
Okay, so this, I did a presentation, I think it was 6 months ago now, on some of the stuff what I was working on. And this is a continuation of that. In that presentation, I talked about the Breadboard, which was an LCD attached to a P2, so I could display virtual hardware in an LCD next to the actual hardware. And since you guys released the Edge, that was a really bit of a game changer. I think that was really good because it solved several of my problems that I've been having. And so I'm just going to give you a quick little demo of what I call this virtual breadboard avatar system. And so what we have here is, in this case, the flip module. And there's two types of avatars, one with just a single chip, and which connects to just any one of these, you know, serial USB serial through things. And then the other one is expandable and based on, well, can be expanded with the P2 to add additional virtual peripherals. So let me just show you what this is about. This is actually a video. So what we have now is in browser, the ability to connect through the serial ports to these virtual avatars. And that brings in the I/O through the avatar interface. So for example, in this case, you can then program the actual live module, the flip module, using, you know, the regular connection, using the regular tool, and the virtual hardware shows in the browser. So I've just got two examples here at the moment. One using just the regular I/O, and one doing an LCD screen. So the idea here is I'm creating virtual hardware that you can connect to actual modules, and they work and look and feel like real hardware using the same code, and you're using these avatar interfaces to basically dynamic logic analyzers, if you like. So the essential one chip version is using these new PIC18F 47Q84s, which have got some really great I/O capabilities with DMA and all sorts of nice things. And so this is what I was starting to create some new libraries for. So this is, Ken mentioned the SBUS. So the idea now is to extend this to handle the SBUS protocol, and then have a, you know, a virtual fly, what are they called, fly things, or whatever, Skyflies controller in the browser, for example. And so that's the single chip version, and this is the Propeller-based extended version. So in this case, I've got two of the PIC18s, and then I've got an expansion bus based on your P2 Edge format. Not quite, it's not quite pin compatible, so these are not Edge compatible pins. But the idea here is I'm using these expansion ports as a way to add the ability to upgrade effectively the types of virtual peripherals that I can create. And so in this way, it's a type of, someone mentioned earlier in the chat, logic analyzer. So it's a kind of logic analyzer, but it's feeding into the virtual breadboard framework in a dynamic way. so you can visualize the virtual hardware. And the idea is to use basically side by side virtual hardware with real hardware. So what you can do is you might have some things which are real hardware and then some things which are virtual. So this is, I guess, the goal of this avatar system. And so at the moment I've got this extended using the I guess the edge or the microbit connector. With this extended version, you create interfaces for different modules. So in this case, this is the flip module. But, I'm also going to be doing other ones, like the microbit and the Arduino shield, and so on. So with the expanded version, this is also got to handle 5 volts. So I've got some pin protection. I've got some hyper RAM on here because I'm going to do video capture if I can. So we use that as kind of a frame buffer. And we've got an SD card, so I can pass that through to the end device. And this is a 3-volt version, which will work directly with the P2. So you'll put the P2 in the end, and then you'll have the expanded virtual peripheral in the module. Anyway, so that's just a brief summary of what I'm up to. And at some point soon, I'll do a more in-depth presentation on this stuff.
James, going back, you showed something similar 10 months ago, right?
Yeah, right.
It was visual programming using touch logic control, and
yeah,
you
the TLC stuff. Yeah,
the P2 eval board, and it looks, and you had graphical icons representing input output. So you've now switched it to spin based.
No. Right? That stuff was integrated in Virtual Breadboard itself, and this is still, this is let's call it, Virtual Breadboard is the system that you use to create these hardware modules, right? And then Virtual Breadboard, this works as either the Windows Store app version, and then I've now got this new feature which allows you to publish these circuits. It's a bit like, say, TinkerCAD, but I'm taking a slightly different direction.
So you use Virtual Breadboard to make or model the input-output devices,
and then you publish those completed circuits to the web, and then you can connect to those through the browser to the avatar hardware as an option. You can also obviously do all of this inside Virtual Breadboard itself, but to support a lot of different other scenarios, going in through this serial browser stuff is really, really useful. Yeah, so these circuits, for example, like this is designed in Virtual Breadboard. And so then you will publish that and then to access it through the browser. So that stuff was called Remotify, and I actually talked about a little bit of that stuff in that last presentation. I hadn't done it yet, but I was discussing the techniques that I was going to use to do that. And so since then, I've actually got a couple of universities using that system now.
Well, now that we also saw Gavin's presentation, and he was using the modeling tool for Arduino, this might be good.
Reluctantly, this would be much better. Yes.
Maybe this would fit that need quite nicely.
Well, one idea there is with this type of interface like this, I'm going to be doing one like that for the edge, where you will basically you'll plug the edge into this and then this into the edge slot, so you can intercept it, so to speak. And in this way, you can piggyback additional hardware that's not already on that board with the existing board. So at the moment, this, in other words, that would be compatible with Gavin's system already, whereby you could then extend it with additional virtual hardware that you could use side by side with the physical hardware that's already on the board. So maybe you want to add an LCD or something else to the kit, so to speak, which you can then also program through the P2.
Oh, I've got a whole pile of parts I'd like to add to it.
Right. And so that's what this is about. And this is what brought me to the P2. And earlier I showed you that development system that I created for the P1, because I was originally going to be doing all this with the P1 to create virtual peripherals, right? But essentially the P1 didn't have enough horsepower to simulate everything. So, for example, I do NeoPixel captures and things like this. And I also do that with this this in the one chip format too as well. So this is actually a really powerful, very powerful little chip, this 18F Q84. But when it comes to doing some bigger LCD displays and things like that, that's where I'm going to be writing these device drivers using that framework for the P2. And that's why I'm busy now upgrading my framework to develop for the P2 so I can develop these sort of device driver capture. So it's the opposite of device driver. You see what I mean? It's like the other side. So you guys write device drivers for your LCDs and so on. This is the other side of this. Is this captures the signals and then basically serializes it and puts it over the wire, and then I then display that inside virtual breadboard. And there's a lot more other stuff I've got, but I obviously just put this together 15 minutes before sending you guys an update. So I would like to do a more full presentation at some point.
Oh, this is great.
So I just understood this. So you're capturing the signals that are actually being generated by these various boards and then showing those on the screen.
Right.
Okay,
So
I was thinking, how are you simulating? How do you know how to emulate all these things? But that's not what you're doing.
No, I'm capturing the signals.
Right. Okay.
And then passing those through to then, I've got a component development kit inside of virtual breadboard, which allows me to build the visuals, and then also it's essentially like a dynamic logic analyzer with visualization.
So let's say you have sorry, I interrupted. Let's say you have some parallel IO control and the P2 or P1's running stepper or 7-segment display code. How does how will you know the difference?
Well, you will design that in virtual breadboard, and where you put the wires, it knows it will dynamically tell the chip to look for signals on those particular wires. So.
But then, James, you are emulating things like LCD displays then, right?
Yes.
Okay.
In virtual breadboard. So it's got a component development backend, which you then, you and depending on how you want to develop a particular component, you'll decide where it's best to do a certain thing. So you will usually do that, like, for example, with this with this thing here, right? So here you're capturing the output of the 4-bit pin system, and you're capturing, the different timings between the different IO changes on the port and passing those to DMA, and then sending those serially to virtual breadboard, which has a decoder for that HD, whatever it is, language, which it then turns into letters and then renders into the LCD screen, for example.
When you capture the data, do you timestamp when changes occur, or do you just make big recordings?
Yeah, so you can also use this, even with this chip now. I've also, like I said, I'll have to do another fuller presentation, but so you can use this as an oscilloscope, for example, because yes, in this case, it's exactly what it's doing. It's using the DMA to capture the timer of the peak, and then it writes the time, and then it does a delta on that, and then it uploads it over the serial, so to speak. So each it's like component driver. Each driver's depending on how you want to do it and what features are available.
I see.
Where I'm attracted to the PIC is because originally I had, this is, if you look back in this, like 2014, I did the first version of this, and back then the PICs weren't pin mappable. So I had this problem where how would I be able to map to different pins if someone wired it to different places? And so that's why I was very attracted to the Propeller in the first case, because you can map pins to any place you like when you want to create the decoder. And but unfortunately, like, the P1 just wasn't fast enough. I could only ever get like 8 megahertz SPI, or for example, the default application was the Ardu Boy, right? So I wanted to capture in full speed the Ardu Boy SSD thing at full frame rates. And I mean, I have that working with this system as well now, but since then, these new PIC18s, the modern family, you've got DMA, and that makes all the difference. So I imagine it's similar to now with the streamer stuff. I haven't got into it yet, to be honest. That's my next big challenge, is to get up to speed with all the goodies in the P2, to make these virtual peripherals to capture all this cool stuff, like bigger screens and bigger LCDs. And I don't know if we'll get as far as video, but we can certainly do some abstraction to slow down like the video stream. If we can't keep up, you know, maybe you'll make one bit change and then you'll slow down the VGA refresh rate and maybe able to capture it that way, something like this. So I'm starting to think about some of these bigger applications, but I still have to build my hardware up yet.
Well, when you're ready to sync up, we'd love to work together and give you some ideas for the hardware to support. I mean, for example, if it tied in with Gavin's book and some of the quick bites that we offer, this really makes a lot of sense to us.
I'll be sending, these are almost ready to rumble. So I'm going to send you guys some of these to play with pretty soon.
Okay.
And I'll give you some instructions on how to get started with it. And then you can give me some suggestions for components that are in hot demand for sure.
James, you said you're using some new version of a PIC which has DMA to do all the capture.
Yeah.
Those are probably pretty inexpensive chips, right?
They're that's why I've got two of them on this board. These ones.
Are they like $3 or $2? Or?
They're only $1. They're like, yeah, they're less than $2 or something like this.
Yeah.
They're really pretty epic, actually.
Yeah, because with the P2 can capture all 64 pins, every clock if you want, but the chip's more expensive.
Yeah, that's why I've got it as a separate system. So I've got this cheaper system, which is the individual single chips on them, which have got less, it can virtualize less hardware. And then I've got this more advanced one, which is going to be able to, you know, virtualize a much bigger range of hardware. But obviously you will only go for this bigger system when you run out of speed. And, you know, you want to do more than what the other one can do.
And that one's based on a P2, is that right?
This one here, the idea is that you've got a 4-channel super high speed USB here, and so it's running individual channels to each of these PICs and an individual channel to each of these 2 slots. And then so these guys are all sharing the bus, so they can all run together. And then this P2 here, I don't know if you can see my mouse moving on the screen.
Yep.
This P2 here is also sitting on the bus. So they'll all share the bus, and it's just running as a virtual peripheral, you see. So I'm not trying to do any fancy coding on there. I'm just using it purely to, like, you know, if I want additional UARTs or additional I2C or additional things like this, and also additional customized virtual peripherals, like things that can capture some of the unique some of these things like graphics card displays, you know, they've got busy flags and all this sort of stuff. So you've got to be able to set those in a timely fashion. Right. These PICs, by the way, have got some onboard logic, which is really handy too. So you can map pins and then have some basic and or logic gates built into them too. So that's really handy. But that's the idea. So the idea is that you'll buy this baseboard, and then this will be optional, but you'll expand it, and then also I'll be able to do different designs of this too, depending on what you're trying to actually virtualize and what you're trying to capture. Yeah, and so then the idea is then you break it out to the different modules through these expanders, and then so for each of these I've got a matching one of these, you know.
Yes.
So that's how it works. But yeah, so I've got to go through the heartache of getting this all running. I had a similar version to this working, so most of it should be okay. But I've got to assemble it and, you know, do that hard yards of making sure it all works as expected. So that will take longer, but this other stuff's basically almost ready to go. So I'm going to be rolling this out really, you know, within maybe even less than a month. But this will probably take 3 or 4 months to really get somewhere, to get rolled out.
Thanks for the update, James. And I was curious, do you have schools in the UK using this already? The Arduino version?
I have schools using, yes, I do the Arduino version. It's the thing that mostly I sell at the moment in virtual breadboard. And I have a couple of universities now using this, one in Switzerland and one in Spain, and using the remotified version, which they run into the same problem, I think, that Gavin has, that they'll get 8 out of 10, you know, 8 Windows and 20% Macs, and then they say, well, what do we do? You know? So having the ability to publish these basic, they were quite happy in their case to publish pre-made hardware and then use it mostly to program. And so, by the way, you can drag and drop. I've got a bootloader link to this too, so you can actually drag and drop. That's why I asked in the forums about whether the this bootloader here downloads over the browser the hardware. Sorry, the firmware for the flip. So one of the things you can do if you're, for example, using this Blockly or whatever, if you can export the binary to your desktop, then it works a bit like a microbit or whatever, that you can then drag and drop it into the browser and use that to program it, for example. So, but this is quite new. This is, I didn't, this web serial stuff's reasonably new. I've seen it come and go from browsers over the years, but they look like they're pretty serious now about keeping it in there. So it's, I've only just, you know, just rediscovered web serial in the last week or so, and was able to punch this together quite nicely. So I'm pretty happy with that.
Well, welcome you back for more detail sharing whenever you're ready, or when you have something we can try.
Yes, I will put together, I will send you out some of these guys.
Okay.
And when you've got them and done a few basic steps, I'll put together a sort of a bit of a getting started presentation, and then maybe we can follow up with you then.
That'd be great. And it'd be really nice to somehow consolidate our focus with P2, so we are less disjointed and then more together where we can be too, so that we can move from the fringe professors that see the light of the ease of use towards many, many professors and educators. It's hard. It's really hard to overcome what's...
In my case, I'm using it mostly as an application thing. You know what I mean? Rather than say a development tool or in a development environment, I'm using it as an application thing. But in doing that, there's obviously going to be spin-off. You know, just in the tool that I'll build to even make it happen, for example. So there's all sorts of possibilities, and even just having people see, you know, why you might use this in particular application is already a useful thing.
Cool. Number one request when the pandemic started was virtual ability to program our robots.
There you go. I just need to make a virtual robot in there.
Yeah. And I would say you just need a robot. Send them home. Good stuff.
I'll leave you guys. Time for some bed.
Thanks. Yeah.
And but thanks for your attention. And I'll catch up with you guys next time.
Thanks a lot, James.
Wow, it's been almost a year we've been running P2 live forums. So now we're seeing progress from people that started things way back when. Anyone have any tech support questions for Chip? Controversial topics about tools or floating point?
Yeah, I actually don't use, let me put my screen on. Yeah, I'm not a believer in floating point. I think it takes up too much time. So I need 64-bit, 32-bit's great.
You were the one that posted that in the forum, in the chat, huh?
Yeah.
Yeah, I like that idea. It's much simpler. But
actually the BacicStamp got me into integer-only maths, and I've never looked back. I just think floating point is a waste of time, literally. So quite prepared to talk about it and change my view, but it's worked very well. Even complicated inverse kinematics, integer only, you'd use Taylor series truncated, works fine, gives you all the accuracy. You have to work out what accuracy you want and then decide what degree of polynomial you want to go to. Works fine, real fast.
Yeah,
And,
I bet it does. I know it would.
Yeah.
Well,
I agree. I was going to say just that trying to teach this to the students that are not used to the idea that math isn't free on a computer is difficult, and it was a particularly hard sell. I'm just pulling up an older lab book. I have a course back I used to have the students buy for many years. So this is an example of a PID algorithm using the floating point objects. And so even the assembly-based ones, it's just so obfuscated to kind of understand what's happening in the PID control when you look at this. So I've had to write pseudocode so I can kind of see this is what it should look like if we had casting and things were simple. When you start dealing with sample times and stuff and you start having to keep track of the fixed point decimal place, it adds a lot more complexity to something that's already complex to teach the students to begin with. So I'm trying to not obfuscate try to distill out the really important stuff without having to get lost in a whole lot of things that are only because the chip we're using doesn't want to deal with floating point in an easy way.
Yeah, Gavin, I got to tell you, you're a breath of fresh air. I can't believe you said it. Brilliant.
So I agree with you in theory that we shouldn't have to do floating point, particularly on a microcontroller chip. It's not something we should do, but the fact is all the competition does it. So, and even like I said, the MSP 432 has floating point hardware to do it natively.
Yeah. You're right about the students. Their mindset is stuck in. It's very difficult to.
They want to hit the easy button, and the easy button is the instructable.com that shows how to make an inverted pendulum with the Arduino, where they just grab somebody else's library, don't have any idea what's going on, but it works. So that's hard to argue with. The fact that really what they're signing up for as engineers is to learn how to make that stuff. So I'd be all for the Arduino if our students would actually write their own libraries and give them to other people to kind of pave the way for other people to follow along. But I think that as engineers, they need to go a little bit deeper and to understand some more stuff. So I'd love to get them all, understanding in depth how to just deal with integer PID control, for example. And I actually did a PID algorithm for the BacicStamp that worked in a similar way. But it's just as they want to get more complicated into controls and stuff, it just adds an extra hiccup that makes things more cumbersome for them.
Yeah, it's two things to teach instead of what you're trying to teach.
Yeah.
Guys, I've got a question for you. So I'm really now want to start using the P2 Edge at this new university I'm teaching at. Want to start to introduce the P2 Edge. I've never liked C. I don't like C. I can't program in C. Blockly I love. I've worked in assembler. So would you say I have to start? I mean, I don't mind at all using Spin for teaching this course, using the P2 Edge. Should I kick off with using Spin? What language should I use to get robot projects off the ground using the P2 Edge?
I would suggest Spin too. I think that's really, it's native, it's easy, it's going to run efficiently. And the thing that I've really loved about the P1, and this is kudos to Chip, is that it's flawless. I've never had a problem where something's gone wrong that wasn't my fault or wasn't a student's fault. So I can always just rely on the machine. I think there's one time where some student was writing something quirky where they had 60 some branches from some statement where I think that overloaded the interpreter. But other than that, there's always been a very logical explanation as to what's gone wrong. So I think it's the kind of bulletproof nature of Spin2 that I really like.
Is your P2 experience the same so far, or have you noticed anything?
One thing I told you about the modulo command having signed now. That was the first time that threw me for a loop until I read the manual. But the other one was that the for loops always post increment after the loop. That kind of threw me for a loop. So is there a reason for that? Usually if I can find out why there's a reason for something, it makes more sense to me afterward.
Well, the way that iterative looping works is, this is when you have a variable that's counting, right? That you can access the variable inside the loop. Well, the first time through the loop, okay, you're thinking, should we evaluate ahead of time before we execute any code versus after we execute once? Is that what you're thinking?
What I'm saying is if I do repeat I from 0 to 9, when I'm done with that loop, it winds up being 10. And that leaves me scratching my head because it seems like it's.
Oh, okay, yeah, because the last iteration, it failed the within test, so it fell through.
So unless there's a real good reason for that, I think that should probably go away, just because that's counterintuitive. Okay. Unless there are other languages that do that.
No, I mean, I could probably make a small change to the interpreter and have it stop on 9.
Am I alone on that? I think the spin 1 did that, would stop on 9.
So does that mean continuing to use the variable outside of the loop?
Sure. I mean, why wouldn't you be able to?
Yeah, I see what you're saying.
Yeah, it's a pattern I hadn't used, because I always think of the loop variable as locally scoped from other languages. And what we're suggesting is that it doesn't have to be, because it's declared outside of the loop.
Well, the upshot of it post incrementing that Gavin doesn't like, but the upshot as I see it is that you can use that value to determine if the loop terminated early or not. Because if it's greater than your loop bounds, then you know that all iterations of the loop happen. But if you had an exit in the loop because of some other condition, the value of your loop variable would let you know that the entire loop didn't run.
That makes sense. So that's the ammo I'm kind of looking for when a student says, "Hey, this is quirky. Why would we ever want to do this?" Or
okay, so another thing there is you've got your loop, and so if you're incrementing through 9 and you end up with 10, it also I think it might be possible to just talk about how the loop works. That hey, it failed the comparison on the 10th iteration, so the way it figured out that it failed the comparison was to add 1. So you have 10, you make the comparison, it fails, and then the loop finishes. And that way the students can see inside the mechanism of the loop and understand that, yeah, the number will be 1 more or whatever increment more after it's done. And then they can just basically take that into account in their code. Kind of like what John said, that 1, they can tell that it's done, that it didn't break out early. And then 2, hey, I counted to 9, now I've got the number 10. Do I need to subtract 1 because I need to continue to keep track of those iterations? Maybe.
Here, let me share something that I just found the code. Let's see, this is the repeat var init. And then here's the loop, right? So the second section is where it does the test. So where it says add x comma c, add the delta into the current, and then it checks for out of bounds down here. And then if not out of bounds, unpop data and loop, otherwise, pop stack and continue, leaving the variable beyond where it was.
Mm-hmm. So I agree with Andy's explanation, and John, I think that, just so long as I can explain a logic as to why it works. So another one that the very few things in Spin 1 that frustrated me was the how to limit the minimum and maximum. So I just already have this code for the PID, so I'll just point it out here. And that always just, was so hard to remember, whether or not the pound sign was before or after the greater than or less than sign as to why those were mirror images. But then I was watching one of Johnny Mac's videos about how you could just put the variable in between these two and then just kind of imagine it kind of like stuck in the way that it would process it. And then all of a sudden visually that makes sense, and I never have screwed it up since. So if there's a reason for things, then it becomes easier to teach and to explain.
As I said earlier, I'm a very visual person. So I look at that, if that hash greater than, well, if you got rid of those 2 vertical bars, it would say equal or greater than. And to Frank, who had a question earlier, the upshot that something that I really like about Spin 2, and that Gavin mentioned it in his presentation, since you mentioned, Frank, that you really like assembly, you can put blocks of assembly into your Spin code without having to instantiate another cog. And I absolutely love that and take advantage of it all the time. I'm not a great assembly programmer. I think I'm a functional assembly programmer. And if you, I don't know if you saw my presentation last week or if you happen to catch it online, you'll see I actually was doing the decoding of the SBUS data. I did it in Spin so I could test my algorithm. And once I knew the algorithm worked really nicely, then I translated it to assembly, and I didn't have to instantiate a cog. I just made another method and put the assembly code in there. And I was very quickly able to go back and forth between the two to test. And for me, that is, and now I say this a lot, so I'm gonna just throw that caveat out. My favorite thing about Spin 2 is inline assembly, but probably in 5 minutes, I'll tell you something else is my favorite thing about Spin 2, because there's so much to like about it.
Yeah, I'll second that. I think, in particular with the really rich instruction set in assembly and on the P2, just being able to dive in and just use that one command that you need, just an inline assembly, it's just, it's neat to be able to break into that. And in Mechatronics, the applications I find for this environment, there's just kind of two different worlds of timescales where you want to have the human interacting with buttons and dealing with stuff, and then you want to have things happening at a scale where you need the ultra high speed, you know, say like an airbag detector, or accelerometer data deploying an airbag. So it really is nice to be able to just, you know, have certain things running bleeding edge in assembly, a couple nanoseconds per instruction, and then, you know, for the other stuff, just to deal with a nice interpreted language that's easy to work with.
Well, that's it. With the Spin, with assembly in the P2, you get the double bump of increased speed of the processor. But what I'm increasingly finding as I'm going through and learning more instructions, several instructions in the P2 will displace, or sorry, there are several instructions in P2 where a single instruction in the P2 can displace 2 or 3 or sometimes more instructions in the P1. So you get kind of a double dip on the speed aspect. You're running a faster processor with fewer clocks per instruction, and the instructions, you know, for example, you were mentioning, Gavin, that you liked, you know, the pin high and the pin low. You know, we all do. I mean, Chip created that. If you think about it, the BacicStamp 1 was the first easy to program basic processor, and that had high and low for the IO pins. Well, we have that again, even at the assembly level. One of the nice things I like, even at the assembly level, is that we can drive a pin high or low, which handles both the IO register and the direction register with a single instruction. So as you indicated, when there was those times when you need very high speed IO, the P2 really delivers.
I mean, it surprises students, but we'll talk about the Raspberry Pi, which processors clocked even higher than the P2, but because it's running all of the Linux kernel and the kitchen sink as well, it just can't blink an LED in 1,000th of the time. I mean, it takes 100 times more time to, say, blink an LED on a Raspberry Pi than it does on a Propeller. So that's, and again, it gets back to what I was explaining too, that the real beauty of this is going to be when people like you, John, and Chip and others write software in assembly for this chip that let it just run perfectly, you know, efficiently and ultra fast to do these things like, you know, HDMI drivers and VGA drivers and RGB LED displays. And it's just, that's really where the beauty of this chip comes in, because even with all the following that the Arduino has, there are just so many people just adding to the pile of mess that is the code that runs a lot of their drivers, that there's really, you know, having people that are going to take the time and love to actually get down into the assembly and program just, you know, pure code to this is really kind of a neat idea.
I have a screenwriting book on my shelf that suggests that in human history, there are 20 essential stories. I think that same thing exists in the Arduino. There are 20 essential examples, and everybody just piles on the same example. From last week, you know, again, when I was doing my SBUS stuff, I said, well, the Arduino family, and it really is now a family. It's not just the Uno anymore. You know, so there's a lot of code out there, but you see the same thing over and over and over and over again. And I feel bad for those people that unknowingly think that, okay, that's the way to go, but they don't. I think your students are lucky. I don't mean to seem like I'm blowing smoke up your skirt, but your students are lucky that you're forcing them to write code and not just use libraries, whether they're mine or anybody else's. I know that you are using libraries, but you're forcing people to write code. And so the presentations that I do, I think like you, I like programming. It's fun, it's joy. It's part of my artistic side. It's why I'm so maniacal about formatting. To me, that's art. And yet it's functional. We have working things. As I mentioned last week, I have 2 friends in show business that needed SBUS. So my art is helping their art. And to me, that's a really cool thing that I could do for them because they're serving their customers. And one of my friends, as I said, is working on Star Wars. So the stuff that I'm coding for him is going into entertainment that I get to watch next year. It's a circle of life.
So actually, speaking of SBUS, I do have an application for that I think might be interesting. I teach a course in Introduction to Aerospace Engineering, and there's this project we've been doing. I've been teaming up with a professor. She's retired now, but she was a former astronaut, Kathy Thornton, and she's created these lighter than air blimps out of helium. And we use spectrum radio transmitters and the receivers, the servo signal receivers. And for years, I've wanted to try to just go back and do that from scratch because we usually have way more motors and stuff than it was kind of designed for. And they're designed to control airplanes and helicopters. So getting them to switch over to be able to control these student-made custom blimps has always been difficult. So I've actually worked out for the P1 just how to just grab the signals after the receiver into the pulse width signals. And but I'm looking forward to digging into the SBUS stuff that you've just decoded for us and trying to figure out how to get that into that course. I'll see if I can dig up a video.
Going back to Frank Nichols' question, though, about what language and what material for the P2, I think it's going to be Spin 2. And I originally thought it would be MicroPython, but I'm not really sure at this point because we need to see that could run other modules. But what happens is now the industry here, Gavin's going to produce a book. So this could become your content for your class, and the kit could also become your content. And maybe that combined with Quick Bytes would be everything you need to know to run a class with it. That's my thinking looking forward. I mean, you're asking what our direction is, and we haven't really talked about it because we've just been so busy doing everything else. So the direction's getting formed by you guys.
Actually, you're reading my mind there, because my next question was going to be, people keep talking about Python or MicroPython, and what should I do about that? So I'll stick to Spin 2 and assembler then, or Spin 2 first and then some assembler maybe.
So again, it depends on where they're going with it. My take on it would be, unless they're going on to be software engineers, we're going to be writing in a language all day, every day, and really be able to understand all the depth and all the little details, minutia of that language. It doesn't really matter as they're getting started. It's like riding a bike. It doesn't matter if they're on a mountain bike or 10 speed. It's just getting the knack of it.
Yeah, I agree, Gavin. What I do a lot though is fast inverse kinematics for multi-leg robots, that sort of thing.
From my perspective, and I'm not a controls expert, but MATLAB really has cornered the market on that. So if they can program it in Simulink, and then with what MATLAB has is called the real-time embedded control workshop or toolkit. It's several thousands of dollars, but basically what that does is it automatically takes your Simulink diagrams and converts it into C code that it sticks onto a target processor. So,
I see. That answers another question too, because my colleagues are now talking about that very thing you're saying. And I'm thinking, well, what's that got to do with embedded processors? So you're saying
it means you focus on the control theory and you don't even worry about the hardware and just let it all compile it down onto an ARM processor for you.
But I kind of like to know what's going on. Okay.
From what I observe is most of the experts on controls don't want to be experts on hardware, and vice versa. So it's kind of, when you're dealing with the abstract level of control theory, digging into the details usually is where people.
I like the hardware. I'm hardware oriented, so yeah.
Now, does that suggest also that since we have FlexBin support for C, that the MATLAB approach will actually work with FlexBin?
Okay.
With the P2. I'm wondering if that'll be the case.
That would be really useful if that were the case. But the whole point of this embedded controller toolkit is to just separate it. So you don't ever have to worry about the hardware. It just, you work it out in MATLAB and it automatically is going to make it work into it. But of course, then if it doesn't work, you're totally in trouble because you have no way to fix it.
Yeah.
So it'd be good if someone had an instance of all of that so we could actually prove that path. Then we know.
I've been wanting to dig into it. We have a site license at the University of Virginia for MATLAB, but not all of the toolkits. And this is the one most expensive toolkit that I think is $4,000 or $5,000 that I'd have to shell out for. But it's something I've wanted to use for a while. But again, it's kind of sad because you don't get to deal with the lower level details, even if you want to.
Yeah.
Sure. But making sure this P2 environment has an adapter for it, if it would work, would be a useful thing.
That would be huge. On that front, I think that it would be fine just as a first step to have it just work on a single core of the P2. I know having parallel processing is going to be more complicated, but I think just getting a single target core would be useful. And in terms of the advertising and getting people on the hook, there's just such a following for the Arduino. If we could have the P2, just a single core of it, be a target for the Arduino IDE, so everybody's kind of on their home comfort level in their Arduino IDE that they love so much, and they can just add in a driver for the downloading to the P2. I think that'd be a huge way to hook them into this.
We can call it paste.
There's no sign of Blockly being used for the P2 then, Chip? Or?
I don't know. Ken would know better than I, because it involves other people.
Mm-hmm.
Right.
Chip only plays alone. Yeah. Frank, it's a little bit early, I think, still, because all efforts are going towards documentation right now.
Right.
And software, and I would just love to have a Blockly for P2.
Hey.
And then the next question, that begs is, which language would it generate?
Well, what would be cool is P2 that runs natively on, BlocklyProp that runs natively on the P2 with an IDE. This kind of narrows the scope of a general development system to something that's like, click and drag the puzzle pieces, fill in the blanks. And Gavin, would that be interesting to you if that were self-hosting on the P2?
Yeah, I think, again, it would solve that Mac problem, but it's not that big of a problem to me, honestly.
Do you ever use BlocklyProp, Frank?
BlocklyProp for the P1, I'm sold on it. I think it's fantastic. And the students that I'll be having will be very diverse in their experience and thinking. Some of them will not have much maths or computing experience. So the Blockly is going to be a fantastic kickoff for them. But I want to get involved with the P2. So I'm just wondering how to play it at the moment. If it's spin, an assembler, it's going to be a bit problematic with some of the students, but I'm thinking aloud now. So I think P1, the activity board, the flip, and the Blockly will work really nice with our students. And as I say, I'll have it in the background, the P2. Well,
Frank,
work on that myself.
I think you're on the right path. Stick with the P1. Because when I first met you in late 90s in Singapore, you were controlling as many servos as you could with the BS2, like 12 of them. And you were doing it effectively. And BlocklyProp will let you do that with multiple cores and more, and play sound and everything else, read encoders and sensors. I think there's enough for what I've seen, at least from what you do, still to use that. And you're not alone. There are so many teachers in this category of, I use the BacicStamp, I like its simplicity, and I looked at Spin 2, nope, it was timed with the, Spin 1 was timed with the release of the Arduino, which we didn't really know. Andy produced a wonderful book. So many educators bought it, but most of the engineers learned from Andy's book. But in terms of education, they either stuck with the BS2 or they went to the Arduino. But there are still many. Python returned some satisfaction to people, but there was a void that we left behind that would have been served very well by a BS3 or a BS3 made with, the P1. But BlocklyProp has filled that niche for a lot of instructors. in a lot of community colleges who are teaching. I think it's similar to teaching programming in the same way Gavin described it. The Spin 2 language is just code. You know, BlocklyProp is the same too. It's a super code. You could generate what other languages you wanted to.
You can also be quite sophisticated with it, I found. So
yeah, I've made some neat projects sometimes with other people's help. You know, metronomes. We have their commercial products made with it. They fly on drones that distribute.
So I had my students start out, and I've actually done this for the last couple of years, because again, I'm trying to teach them to become kind of language agnostic. Google, you know, has this thing for learning Blockly, and so I have them do the turtle, kind of like the logo that I'd used back in the 80s, where they basically learn how to program with the Blockly, and it shows you the JavaScript too. So I mean, they can actually start to learn the more advanced programming as they go. But my argument is this is riding the bike. You know, once they understand the concept of a for loop and how that works, then it's really not that much of an extension to go to repeat I from 0 to 3 or something instead of this. So it's really all the same stuff. So I don't think that, you know, yes, if you want to say, okay, well, we're actually going to learn Python or C++ or C, then you actually get into a whole can of worms. But if it's just the basics of programming, it's very simple to hop across between one and another.
Yeah. Yeah, good. That's answered my question. Because people are always talking about this code, this language, that language. And I'm thinking, isn't the most important thing is the algorithm? Is the way where you figure out, you know, how to solve a problem and then just use the language that.
Again, that's why I like the riding the bike analogy. You learn how to ride a bike, and but just about everybody's done it. So everybody understands the connection here, the parallel. But it's if you had to tell somebody how to ride a bike, it's really difficult to do that. So if you had to tell somebody how to program, you know, it's just getting the knack of it is something they have to figure out for themselves by falling off and bumping and figuring out what works for them and what doesn't. So I think that's where it doesn't matter if it's a mountain bike or a 10-speed or some other type of bike. It's just getting the knack is what they need to get the hang of first.
Yeah, good analogy. Yeah.
The teaching side of me agrees with that too. It's agnostic, it's just code. And that's really what I believe. But the marketing and business side of me makes me stuff Python in everybody's face. Our number one product is the Cyberbot. Okay. So we sell an awful lot of those robots. There are 20 of them on the desk behind me, and we can't make enough, actually. It's our number one product. And Python has a lot to do with that because it's just popular. But these are first experience coding teachers. They've not had the experience of that all of us have had of seeing things the same way from any language perspective. So I think, Frank, BlocklyProp is still my favorite tool.
Yeah, good.
Love it.
Yeah,
Gavin,
thank you for that, guys. Yeah.
Gavin, I want to thank you. I'm a longtime software engineer. Your explanation of why language agnostic is important for what you're teaching was the first time I've actually thought about that in that way, and it's totally meaningful.
The bike analogy
for clarifying that.
See, teaching is what I do, so I've come up with lots of analogies, and this will all be in the book, so I'll try to help guide people into the right direction.
But learning assemblers like riding a unicycle.
Yeah, probably true.
Yeah, so my analogy there is it's kind of, I look at the course, and this is why I'm calling the book Exploring Mechatronics. I'm really trying to teach people to go off and understand it's kind of like exploring, a forest or wilderness, and the Arduino is kind of like people have already paved the roads. You basically just throw on a pair of flip-flops and you can easily just walk around not worrying about twisting an ankle. But if you want to get off the beaten track and try to start doing things on your own, that's more like lacing on a pair of sturdy hiking boots. And that's kind of where I see the Propeller 2 as being. It's just, it gives you the ability to really go wherever you want and the tools you'll need to not break a leg or twist an ankle on the way. So I think that's kind of, because it's hard, because the students say, hey, I just want to throw on a pair of flip-flops and walk around on a sidewalk somebody's already paved. And and for a lot of people that use Arduino, that's great. I mean, it's a lot of artists and makers and people that just want to get something working, and they don't really care about how it comes together or how it works. But for the engineers that I teach, it's really important that they, again, have that agency to understand what's going on so they can control it and decide their own path and not just follow somebody else's path, following somebody else's footsteps.
Hey, Gavin, do you think about all this Arduino phenomenon where people, cut and paste and put stuff together and maybe don't care about how it works? Do you think that the whole experience stimulates them to want to know more, or does it kind of close up their thinking, because they might suppose, well, this is just how things work. You just stuff stuff together, and then if it compiles and runs, then that's okay. Is it stimulating, like, is it whetting